Very warm welcome to the day 3 of the second winter school organized by MPCST and IIT Indore and IIA. So it's a very immense pleasure to invite Dr. Professor Annapurni Subramaniam to give a lecture as a part of this winter school. Professor Annapurni Subramaniam is the director of the Indian Institute of Astrophysics, Bangalore. She has about 3 decades of research experience and has published about 150 research publications in topics related to stellar clusters, stellar populations, galaxies, and ultraviolet astronomy. She has guided a large number of students, among which there are 10 PhD students. She has been involved in 2 major projects, one being the UV Imaging Telescope or UVIT, which is on board India's first space observatory, AstroSat. She is the calibration scientist of that, and she has compiled and predicted its performance before launch, planned, and completed the calibration after its launch. She has also developed a mandatory user tool for safe observations on of the telescope. She is also the leading scientist of the Indian team of observatory software and completed the common software in 2019 for the 30-meter telescope, which is one of the mega missions India is involved in, which is being built by an international consortium all over the world. She is also the recipient of various prestigious awards and fellowships. She is the Fellow of Indian Academy of Sciences, the Fellow of the National Academy of Sciences, a life member of the International Astronomical Union and the Astronomical Society of India. She is also a Kavli Fellow, which is instituted by the Kavli Foundation in the National Academy of Sciences, USA. She is also the recipient of the very prestigious C.V. Raman Young Scientist Award for Physical Sciences from the Karnataka government for the year 2018. So with this, we extend our very warm welcome to Professor Subramaniam and thank her for agreeing to give a talk as part of this lecture series. Over to you, Professor.
Yeah, thank you, Manita. So shall I start the talk? Sorry for joining a few minutes late. I got stuck in the traffic jam, which has started back to normal traffic in Bangalore. Now, am I audible? Just checking once again.
Yeah, you are
Yeah,
audible.
okay.
The slides are visible.
Yeah,
I think you can start. Sorry, I
yeah,
couldn't
sure.
receive your call.
No, no
My
problem, no
office
problem. Yeah.
has no network of the.
I was just trying to call when it was stuck in the, I mean, in one of the signals. Yeah,
Yes, yes.
between the signals. Yeah. So, stars. So I just wanted to um, so is this blocking the, I think this is better, right? So this doesn't block my view then. Yeah.
Yeah.
Okay. So my topic is stars, their classification and structure. So as I think the participants of the workshop may not have a big major background in astronomy and particularly on stars, I plan to give you an overview on what stars are like and why we should study them and why are they important. And so I just will start with a picture which is basically the night sky. And night sky, you can see a lot of stuff that is getting basically they're projected onto the sky, even though they are at different distances. So when I mean, from way for a few hundred years back or thousand years, thousands of years back, people have started looking at the sky. But with modern instruments and telescopes and detectors and various types of receivers, we are able to understand what they are, why they are there, how they are there, and various structure of the universe, etc., etc. But for everything, the building blocks are stars. As you see in this is the night sky, and this is the pattern which you see here is the Milky Way, and all these stars, the dots out here, are all stars which are part of our galaxy. Now you can also see two cloud-like structures out here. These are the two neighboring galaxies, large and small Magellanic Cloud. And even though you see them as patches, the decent telescopes, like if you up to, I mean, 1 to 2 meter class telescopes, even that can resolve the individual stars in these galaxies because they are nearby. But if you have galaxies which are quite far away, beyond the local group 1 megaparsec, etc., you cannot resolve them. You will start seeing them as patch. I'll come to the next slide and show that. You also see comets, which are part of our solar system. So what happens in the night sky is everything gets projected. We loses the information on distance. All that we can measure is the intensity of radiation in any particular wavelength, depending upon the position of that particular object in the sky. And what astronomers do is that measure its intensity in various wavelengths and study its properties. So in the quest of trying to understand why these things are there and what are they doing there are various types of measurements which people do. One is obviously position. So positions of these stars are cataloged, the various objects are catalogs. So obviously when people start working on anything, they start classifying the objects, whether it be biology or physics or chemistry. The classification is where we start with. Once we classify them, then we try to understand what these classifications are due to and what is the fundamental physics involved in them or fundamental properties between them and what makes one into the other, what separates them, etc., etc. So in the process, the initial studies have been looking at, cataloging the stars. So that is how the magnitude system has come into effect, where you can actually see that the brightest star is 0 and the faintest star with the naked eye becomes 6. So it is actually an ulta system where the larger the number, the fainter the star is. So that is the history of magnitude scale for stars. So stars are fundamental building blocks. Not only that, we also will see that they also produce the chemistry which we see around us. Okay. So going to the next slide, this is how a galaxy would look like. I mean, it's a faraway galaxy. There's a whirlpool from Hubble image. You cannot resolve individual stars. You see all these kind of dots, which are actually groups of stars. So what we see as dots are actually star clusters, and we also see the different colors put in here. The red dots indicating the emission in hydrogen alpha, which is basically indicative of ionized gas present there. So in a galaxy, you have stars, you have a lot of gas and dust, which is actually shown here by dark patches. And the patches are dark not because there is no light there, it's because the light which is it is casting a shadow. That is, the light which is coming from the background is absorbed by some molecules, and these molecules we call them as dust. These are part of clouds which are predominantly molecular hydrogen along with other elements also present there. So a constituent of the galaxy would mean the cold gas, dust, and young stars and old stars and the like. So these things are held together in the gravitational potential of the galaxy. And the overall in very large time scale, the galaxy structure by itself doesn't change, but over a period of time, few billions of years, the gas gets used up, etc., and the structure does change. But the stars are always born as long as there is material present, like the gas is present in them. So there are new stars being formed in certain galaxies. In some galaxies, the star formation is completely stopped. In such cases, they will have only old stars and not the young stars. So the stars are classified into two things. This is actually the structure of the the galaxy itself, the galactic structure. These are the components. This is the large halo, which are actually shown as dots. They are not stars. Actually, they are globular clusters, and they are part of the initial kind of infall. And the clusters were formed, and these belong to the initial population, which we call as the population 2 stars. Though there is supposedly a population 3, which is prior to that, we haven't detected them, but it's predicted. And when the whole cloud gets an angular momentum, it settles down and becomes a disk, and the later on population 1 stars are actually formed in the disk. So the sun-like stars and all the young stars, which are then the Orion molecular cloud, etc., they are part of the disk. So we have halo, which corresponds to old stellar population, which are also chemically poor because the initial stars. I'll come to that shortly. And then there is a bulge, which is actually quite dense with all varieties of stars, and it is pressure supported. And the halo moves like this, like all elliptical orbits with a galaxy center as the center of mass. The disk is actually a rotationally supported disk. and young stars keep forming there. So there are the various types of stars which are formed, and they differ in mass, age, and chemical properties. So we need to understand them to see how the galaxy has been producing stars, what type of stars, and how do they become build, which are the different types of building blocks we have in various types of galaxies. Now, that is what I said. So even in our galaxy, you can see the patches out here. This is the towards the galactic center. So this also says that there is a uh, ongoing star formation happening in our own galaxy. So we can call as the content is stars, gas, and dust. It has got a structure and it has got kinematics. It has got dynamics. It's got ecology in the sense that there is a churning of matter coming into stars, and the kind of stars giving back whatever the processed material back into the ISM, etc. So we have star formation, chemical evolution, dynamical evolution, interact with neighbors, and the galactic center. So all these are part of our galaxy, but then each and everything is we have to trace, and also we study and we find what is happening with the by studying the stars which are part of the galaxy. So that is how the stars become building blocks. And how to study them in from coming to physics, we normally take the stars as black bodies. So black bodies, the properties is a perfectly absorbing body, and also perfect emission by the object, and it is characterized by its temperature, such that the hotter the body, emission peak, lambda peak, is towards the shorter wavelength, which is the high frequency. And it all not only that, the total emission also increases. So that would mean that if we compare the stars to the kind of black body, assume them to be black bodies, that would mean that the stars with lower temperatures will peak. The peak emission will be at a longer wavelength, and total energy emitted will also be quite low. But on the other hand, if you look at a higher temperature star, its peak emission will happen at a shorter wavelength, and a total energy emitted will also increase. So this is the Wien's displacement law, and these are the examples of two temperatures and where it is peaking. So we take help of this fundamental laws to understand and the overall properties of stars. And now this is also the Stefan Boltzmann law, which helps in saying that the total energy emitted is sigma T raised to fourth. So that is what is happening here. The total energy goes up fourth power to the temperature. So therefore, the hotter stars are also emit a huge amount of flux compared to low temperature stars. And this also helps in understanding flux emitted per unit frequency, which is shown here. So these are the equations, fundamental equations, which are used to understand the emission itself, and this is also a coming part of it. So emitted with respect to wavelength. All right. So what do we have? So the stars are nothing but ionized plasma. It is actually not solid, not liquid. It's plasma, completely ionized. And depending upon the surface temperature, the star can be that is what we measure. We're not measuring the internal temperature of stars. What we measure is the surface temperature of stars. And from the overall radiation is coming from a continuum spectrum, because it is scattered. And if there are ions present, and from the continuum, each ion start absorbing, and then you start getting an emission, because the hotter interior is emitting the photons in various energy range. And if there is a atmosphere where you have a which is slightly cooler, you have an ion that picks up the absorbs the energy and goes up. So which ends up in having a absorption line spectrum. That is, the electron goes up to a higher level, so you end up having an absorption spectrum. But if you have a nebula like the one which we saw here, like in these in over here, this nebular lines, which are basically coming from hydrogen alpha emission lines, which is actually a hot gas which is cooling down, then in which case the electron from high energy state will emit a photon and come down, and that emission appears like it doesn't have a continuum, it will have an emission line spectrum. So there are three types of spectrum: continuum spectrum, emission line spectrum, and absorption line spectrum. In general, the absorption line spectrum is imprint on the continuum spectrum. So we use the absorption line strengths as well as the continuum information to understand what the star is or what the properties of the star. So the continuum spectrum shows the amount of flux. If you measure the intensity across this line, it tells you which wavelength or which color the intensity peaks, which is actually a proxy to understand the temperature of the star. So that gives you a temperature. And you measuring the ionization status of these lines also gives you a temperature effect. Not only that, the finding out the strength of this absorption lines tells you what are the kind of ions present in the photosphere. So that tells you the abundance or the chemistry at the surface of the star. On the other hand, emission line spectrum of nebulae or any ionized material also tell you what are the kind of lines present, which tells you the ionization state and the electron density, etc. So what I'm trying to say is that astronomers use these techniques, which are basically physics, and extend it to areas which are not present in the terrestrial region. That is, the temperatures observed here in the case of emission line spectrum would be more than 10,000, so 20,000, etc. In the case of absorption line spectrum also, the temperature range varies a lot. So basically the physics used is quite a bit of laboratory physics and atomics and molecular and nuclear spectroscopy kind of a thing. So this is the kind of stellar spectra, in generally continuum plus absorption. And so in general, previously you used to get photographic plates like this. Now we use a similar thing, but on a digital CCD imager or something like that. Then you can convert it into counts, and these are called the intensity drop. So what happens is, this is the expected number of photons, and because there is a ion present, it absorbs that particular photon, and that for the intensity of that particular wavelength or energy drops. Now, it's very important to see that the pattern of this particular thing, it is not a delta function like a one line, it is broad. So these gives a lot of physics regarding the surface, because if it is broad, that means that the absorption is happening at not only one wavelength, but plus or minus some wavelength. That is because either the ions are moving, or the star itself is rotating or something like that. So yeah, a lot of information is obtained by looking at the structure of these lines as well. So we get chemistry from looking at the spectra. We get the surface conditions, gravity, etc., gravity of the star, which means the radius of the star, etc., by looking at the spectroscopy. Now, these are the different classifications. So stars are classified. Maybe I should go here first. So this is just taken from Wikipedia itself. And stellar classification based on spectroscopy was done in late 1800s and early 1900s. And it is called the Morgan and Keenan classification. But I should mention that Annie Jem Cannon contributed a lot to this, and she's given a bit of credit, but not in the name over there. But what they did initially was that this is the HR diagram. I'll come to it later. But then the classification was used as we can measure two things. One is the brightness, as I said mentioned earlier, and second is the temperature. So once you actually look at the this kind of things, you can see that the stars over here, as you go down, they become brighter over here. That which is and fainter here, which is blue is fainter and the red becomes brighter. So if you go down from this end to this end, this is brighter, and then gradually this becomes brighter, and gradually this becomes brighter, which means that the redder wavelengths are brighter over here. So this is actually a sequence of stars which are put together from hot to cold, because these stars are relatively cooler compared to them. Now the point is that you have said that these are the kind of stars which have the peak of the distribution is coming here, like I said here. So if you go from here to here, the peak is red here and peak is blue here. So basically that particular graph was like you are starting from hot star to going to cooler stars. Now that is the classification, but you also have to quantify it. What are the temperatures? Now temperature quantification comes from looking at the lines. So at what temperature, what element will start showing ionization completely, and what species will start showing ionization, etc. So that helped in quantifying the temperature. and the emission peak helped in identifying, grouping them. So this is the classification based on temperature. So you have got the temperature on the x-axis, and they plotted the brightness on the y-axis. So on the x-axis, you can say that the hotter stars, which are like bluer, to redder. So they classified them as OBAF, GK, MLT, and that is the classification of spectral. This is also sub-classification, luminosity classification needed, because even at one temperature, let's say K type, you can come to various type. Lots of stars are there which have similar temperature, but the spectral lines is different. So if you, that is why I said pay attention to these lines. So the kind of lines you see, even though the continuum has a particular slope, that is due to the particular temperature, particular black body, the characteristic of the line seems to be different. So then they realized that something else is there apart from just the temperature classification, which became later known as the luminosity classification, and that was also related to the total brightness of the stars. So the luminosity classification was coming here. So basically, spectral classification is the temperature classification, and luminosity classification is according to the y-axis. But later on, by after the HR diagram was developed, we came to understand that these numbers of 1A, 1B, 2, 3, etc., 4 and 5 basically corresponds to an evolutionary sequences, and that is why they have that kind of the absorption lines are structured that way. And so HR diagram was able to help in identifying why these have these kind of classification was there. So now moving forward, so that is what I said, the luminosity class. So you have supergiants, giants, and subgiants and main sequence stars. The sun is over here, it's on the main sequence. So this is again, there are also subclassification within the O type, B type, A type, etc. And now measuring their peak temperature, peak luminosity, you can also estimate the temperature. So the temperature also given here. And as in practice, which is followed, this is basically a practice which was started. This is the HR diagram where the temperature goes this way and the luminosity goes this way. So luminosity is okay, but normally the x-axis increases like this, but here the temperature in the x-axis increases the other way around. Now, going to how stars form and evolve, and why, how do they contribute. This is the galactic ecology. So if you look at this, you can see this is a atomic hydrogen clouds which are there in the galaxy, which is basically in the plane. Now after they cool down, they become molecular and they become dense and cold, and cause the clump starts forming, and then they collapse under their own gravity and form stars. Now we have seen the pretty pictures of star formation in various star formation sites, including the Orion Nebula, and stars form there. And after a while, we also see that the stars die. And one of the spectacular end states of stars is the supernova. And supernova explodes, and you can see not only the end product of supernovae sometimes is neutron stars, but we also have seen a lot of supernovae remnants as nebulae, which have told us that the supernovae remnants are coming from the material which is thrown out from the star, and it has a lot of different types of chemistry involved, and that those material which is thrown out during the new supernova explosion gets mixed along again in the interstellar medium, because the stars and gas coexist, and then again the next generation of stars formed will have traces of the remnants from the previous supernovae. So as in when this star formation cycle, star cycle turns, every next generation of stars formed will have the products enriched by the previous supernovae remnants. So, which gives us an idea that as and when the time progresses, the pollutants keep increasing. So you have more and more number of certain types of elements depending upon what type of stars the remnants you're picking up. Now this is supernovae type 2. There can also be supernovae type 1 or AGB, different types of stars. So different types of stars end their lives differently. I'll come to that. And then those gets mixed up. So what we are seeing is that as and when the galaxy evolves or time progresses, as in when the newer and newer stars are formed, the previous stars would have left an imprint on it. So depending upon how much gas is available and how fast this cycle of star gas star cycle turns, the amount of pollutants increases. So that means that the chemical enrichment or enhancement will depend upon two things: one, gas present, and two, the efficiency by which the galaxy is able to convert star to gas. So this, how can we study how much of enrichment has happened? Like, let's say in around the sun, then we study the stars around the sun and also study the chemistry of material in the solar neighborhood and see that what has been the chemistry of the star when at its birth. So we know that all the chemistry, all the elements came from stars which lived prior to that. Then we actually put together that if these are the elements they are present, then these type of stars should have existed before, prior to the formation of formation of sun, and these have contributed similarly. And this is another form of sorry, I'm not able to close this. Okay, all right, got it. This is another form of diagram where it shows that by the star formation, you have the stars in the main sequence. Some of them become red giants, which are less than 7 solar mass. They become planetary nebulae. Some mass get locked up as white dwarfs. But they kind of put in carbon, hydrogen, oxygen, etc. into the next generation molecular cloud. So it goes for recycling here. But the bigger stars actually became supernovae, and then they feed in these kind of elements into it. So you know that what kind of elements come from which type of remnants and get fed into it. But some part of the mass gets blocked, which are not available for next generation of star formation. So this cycle keeps turning everywhere, and that is happening in all the galaxies, and also in it's not the same in different parts of our own galaxy. The same environment may not be existing in closer to the center of the galaxy or far away from the galaxy. So how do we know that? We have to study the stars to find out what has been the past in terms of chemistry. Now, what happens in the to reiterate, the stellar nursery produces stars. The low sun-like stars go into a red giant and planetary nebulae and white dwarf. On the other hand, the stars which are going there as red giant, supernovae, and neutron star and black hole. So both these produce lot of filamentary structures in the interstellar medium, which is well studied now, and we know that these are the main reasons by which enrichment happens through remnants from stars. So basically stardust. So, so how do we know? How do we see if we look at the sky or look at the cluster? How do we know what are the stars? Where are they located? And can we classify them? And can we link them overall? You know how they are going from place to place, etc. Now we have classified them. We know that there are properties between different types of stars. We have a classification with respect to temperature. We have a classification with respect to luminosity. Can we all put them together and understand in one particular plane? So that is what is done by Hertzsprung and Russell independently early in 20th century. So what happens here is that um, uh, you put the star and luminosity and surface temperature. Here you don't generally use spectroscopic data. You can actually use temperature from color temperatures, just like V minus I, which is basically I don't know how if you all are familiar with filter systems in photometry, etc. What basically one does is just give me a second to just make you understand if you're not familiar with it. So here what happens is this is the lambda, right? So how do you know that which star follows which temperature? Do you have to trace all these data points, like measure the flux per unit lambda at all these points and plot everything together to get my temperature? No, not necessary. One point is enough. Or what we do in photometry is basically you don't even need the spectrum. All that we need is a slope. You can see that if you take this, let's say 5,000 to the 10,000 range, and you can see that the slope of, let's say you to take one lambda 1 here and another lambda 2 here. Now you plotted 2 points, 1 point here, 1 point here. Similarly, 1 point here, 1 point here, 1 point here, 1 point here, one here, one here, one here, one here. Now you can see that the even between 5,500 to 3,500, the slope is completely changed. So this is a trick where we define a filter. Filter is nothing but a lambda bandpass of delta lambda centered around V, let's say something around 5,000, and I around 9,000. So this is nanometer, so 500 and 900. So then take what is the flux around this? So just area under that particular point, area under this point. So you have actually a lambda 1, which is a flux corresponding to lambda 1, flux corresponding to lambda 2. Now the ratio will give you the slope, and that is a proxy to temperature. So you don't need a spectrum like putting each and every star in the spectrograph and taking it. You just take an image of the sky in a particular filter like lambda and another lambda. So you can have two lambdas, just the ratio will give you the V minus I. So just very, very efficient. So you can do for thousands of stars or, millions of stars. So the most important part of there is that the reddening, interstellar reddening will play a role, which you have to, I mean, I'm not going to cover that here. And also distance reduces the flux, right? So 1 by r square law. So using Hipparchus, which was in the 90s, they measured the parallax, this is using parallax, and they corrected for the temperature, and this is the absolute diagram. So now we see a pattern like this, and then some stars here, and there were some stars here as well. So now we identify them as this kind of a sequence we see, which actually is populated by the majority of stars. We understand that as the main sequence. Now, main sequence basically means because that's the main sequence in your pattern, whatever you got. So what does that main sequence means? So though it just says that this is the most prominent sequence is all that means, but um, in the over a period of time, main sequence has come to understand this. It means that a sequence of stars where the stars produce energy by burning or fusing hydrogen to helium. So that is what the main sequence means, but it is just like a colloquial word. Sun is out here, Sirius is here, there, etc. This is the blue stars, which are actually hot, and then this is the relatively cool star. So this is the sequence where all the types of stars are there. The main difference between the properties between the stars are that they have different masses, but they're all doing the same. The energy production is basically coming from the same physics, which is the fusion of hydrogen to helium. Now we see this pattern, this going out here. These are the giants. We know that this is how it's going to be going like this. And these are the one of the example of a giant is Aldebaran. And then you can see some pattern of very few stars here, which is coming part of supergiants. And Antares, Betelgeuse, part of Orion constellation, are all part of the supergiants. Now we also have some white dwarfs out here. Now this is a outdated figure from Hipparchus. We have similar figures from Gaia, which is the latest astrometry mission, but I'm not showing that figure here. So these are the different types of stars, and filling out the HR diagram with various types of stars. Supergiants are spread out here, and various types of stars, Vega, Regulus, Sirius, Altair, etc. here. So whatever stars you see in the sky as part of constellations are part here. Sirius is there. It has got a companion. It is a wide dwarf companion, which is out here. So this is how we understand the reasons. Now we see how a star, what is it, the connection between giants, supergiants, and main sequence and all this. So are they moving from one place to the other, or is it an evolutionary, can you create an evolutionary sequence of all these put together? So that's what we are going to see, what holds the stars up and what powers the stars. So sun is generally looking at as taken as the key. So when you create a stellar structure model, or which predicts the stellar evolutionary model, all of them go to say that I have created some model with some modifications, but it has to fit into the stellar parameters. So to predict exactly the same temperature and luminosity, and at what the flux distribution it has to produce. So it is always the cornerstone or your calibration point to make it. And we also understand stellar interior by using seismologies. So we understand that it's got a core, and it has got a radiative core, and there's an interface layer, and the outer layer is convective. We see the bubbly outer surface of the sun, which means that the outer layer is convective. So that also energy transport across core to the surface also plays an important role to understand, which all comes from our own physics, basically radiation and convection. So how the energy transport happens, and efficiency with respect to pressure, density, etc. comes into play here. So these are the type of gravity tends to squeeze a star into a smaller object. What is the tendency? Basically, when the energy produced due to fusion, it supports against the infalling star. So that gives the stability. Now, I should also say that once the star is formed, till the final stages of its evolution, the two things actually compete against each other. One is the gravity, ever-present gravity, always trying to squeeze the star. And every time it squeezes, if that inner material heats up and able to produce its own energy by a form of fusion or anything, then it can stop the halt. So every time the initial process, it forms a star, the hydrogen fusion starts, it's able to stabilize. Now, what happens is that is the main sequence star. So let me just give you an example here. So anytime you put a pressure inside, the heat increases, the energy production increases, the star tries to come back. Now, if it comes back, it cools down the energy reduction, then the gravity goes in. So it's basically a balance between infalling gravity and the pressure coming from the energy production. So this supports each other. But when one overwhelms the other, the evolution of the star starts. It starts moving from that particular point in the HR diagram. So that is how we understand that the HR diagram entirely is located by patterns, and these patterns say that certain periods in time the stars are in equilibrium, like the nuclear energy production and the gravitational pull are balanced. So the time scale at which the balance stays for a longer period, you see more number of stars. If the time scale, the balance happens only for a very short period, then you don't see stars there because it's hard to stay there longer. So that would mean that the main sequence is a sequence, it's a predominant sequence, because this balance stays for the longest period, and at that process, and that process being the fusion of hydrogen. So that is why you have a sequence. And now next major thing you found was in this diagram here, giants. Now, giants, as we understand, is that when the star has a helium core, and the helium, that is hydrogen, is converted into helium. I'll come to that. So this is the second. You just remember that this is the next second halt where you get the most number of stars. So what is that? Why is it happening? That what is making that particular phase stable? So this is stable because the nuclear energy production goes on for a longer time, and then the energy production is able to balance the gravity. Now something goes off, and then they go and settle there in this place, and then everything, we understand that the white dwarfs is the end stage. So now let us see how it goes from here to here. um, Yeah, so how do we understand them? We cannot observe a single star going through its whole life cycle, right? Because it's a very long period. What we do is we study star clusters which actually shows have different ages, and then allows to construct a complete picture. And now I don't have time to explain everything, but then if you have a chance, you can go and look at the HR diagram of clusters, which actually helps in understanding, and not even understanding, but also in testing evolutionary models, and making sure that observed parameters are taken care of. So this is what happens: pressure out, gravity in, and the when I think I have a slide, I'm sure. Yeah, so you have a hydrogen, actually let's say red is hydrogen. In sun-like stars, what happens is you have a red core where the sun is the hydrogen is burning to helium. Now once the helium burns, the helium is it's all gas, right? But the helium is more heavier than the hydrogen, so helium starts sinking to the center. So now you're building up a small helium core. Whatever is converted into helium will just move down because it is heavier. So you will start helium will start sinking, less and less in hydrogen inside, and more of helium. And then the helium hydrogen fusion will start occurring on the around the surrounding the in more helium rich material. So the material in the core becomes more and more and more helium rich. It'll reach a stage mostly like about zero point 0.2 solar mass or something, where it's more of helium, and that at that particular juncture, the the gravity takes over. It is not producing anything inside. The hydrogen starts fusion outside, and this non-burning or non-producing any energy producing core of helium starts collapsing under its own gravity. Now, when it collapses, the potential energy is released, half of the potential energy is released, and this envelope starts blowing up. So that is how it becomes red giants. Now, this can go on till this is the time scale for various phases, but this can go on till the helium core, this brown thing, keeps collapsing, and it ascends the red giant branch. Now goes along the red giant branch, and at a certain point, at all this evolutionary sequences, this is burning, converting hydrogen to helium, and this helium keeps dropping in here. So it reaches about point to another point to solar mass is added between the tip of the main sequence to the tip of the red giant branch, and at that time it can actually, the heat, it becomes so hot that it can actually start the fusion, and when it starts fusion, it actually converts the helium to carbon. Now that is that is the, then it is actually a solid reaction going on, fusion reaction of converting helium to carbon. That is called the helium main sequence, and that is actually another dense region, that is the red giant region. So when you look at the red giant region, that is dense because it is, we now understand that the stars over here are converting in their core from helium to carbon. Here it is hydrogen to helium on in the major, the first main sequence, and these giants are basically converting helium to carbon. So that is why this is also another second stable state. And after that, some of them don't have enough matter to collapse again and continue the further evolution. Those stars which are like small, one solar mass and up to about 1.2 to 1.3, they actually the core becomes a white dwarf, a degenerate white dwarf, and then goes helium white dwarf, sorry, carbon white dwarf, and goes. Certain things don't even able to go up there, come down. So we see them in globular clusters, very low mass stars, less than one solar mass kind of a thing. And stars which are more massive than 3 4 solar mass go into the supergiant phase. They actually come down again, and then after the carbon core helium fuses to carbon, and the carbon again becomes able to heat up, it starts fusing again. They go through an AGB phase, etc. So these are for higher mass stars. So what I'm trying to say is that, so these understanding stellar structure and evolution has helped us, and also the location, a classification, have given us an entire picture, in the sense that stars, when they form, they fall on the main sequence, and once they follow the main sequence, we know how the stars evolve, which are the evolutionary phases they will go through, what all elements they will produce, and what are the likely output from such stars to the interstellar medium. So we can actually, if we put a star in this, measure its luminosity, basically the absolute magnitude, and temperature or color, you can actually say that which evolutionary sequence it is going through. So Hertzsprung-Russell diagram, which is actually started off with putting the labeling stars in various sequences. Now, with the understanding the stellar structure and evolution, we have actually able to visualize or say predict things, how it's going to move. So it is completely integrated, the classification, their location in the fundamental plane, etc. together. Now, I think I'm almost done. So this is also a table of um, what are the different time scales, and what are the different radius, etc., and what are the central temperatures. You can see the thing out here. So as you said, the main sequence has the maximum time, and if it's unlike star, and then the next one is the subgiant branch, then the helium flash. Then you can actually, the horizontal branch is about this particular thing. So here what happens is, in a globular cluster, I can show you that the time scale for which is actually quite large. So it is similar to it, but for larger mass stars, this becomes very small, and they vary at different phases. The radius and other temperatures, the central temperature, surface temperatures, all vary. So this is how it moves. So you can see that these are radii. This is luminosity and surface temperature. So if you can see that the star, this is the main sequence. The star starts off from here, and then it goes to the subgiant branch, and this is the red giant branch. So these are the kind of luminosity it will go through, and this is the temperature range it will go through when it changes from here to here. So when it goes to the red giant, it is at here. So you can see that starting from 1 solar radii, it has gone to about 100 solar radii. Now, at that time, it is actually helium fusion, and it converts hydrogen to carbon, and it comes out of the horizontal branch. It is basically for sun-like old stars, and this will be the kind of I'm repeating that thing. So this is basically a carbon ash, carbon which is produced from the helium, and then you also have hydrogen shell, and then the non-burning envelope. So you'll have layers of various things. And when you have a convective layer, it starts producing things from inside to outside. So we start seeing different types of chemistry on the surface. And that is how we know that such things are happening in the interior. So if the star has enough mass, it'll go from here and again to another like this. It'll expand again. That is the carbon core contracting. It can be a neon, or if it is not able to ignite, it'll continue going up here, but then it'll start contracting, and then it becomes a it lifts up the outer envelope, and it basically becomes a white dwarf. So that is how the evolution comes for the low mass star. So you can actually see that the from the star protostar, it was little big, bloated, then it became a main sequence star. It lived for a very long time. Then it became a red giant, and the core got exposed, and the rest of it got lifted off, and then it becomes a white dwarf. So this is basically how we understand. And we also have various types of variable stars, which falls on the variability can be of two types. One is intrinsic, the other is extrinsic. The intrinsic variability is coming from the star itself starts pulsating. That is because of an ionization layer coming in the front, in between, which acts like a sink. So it pulsates. These are called Cepheids and Array stars. We also have stars which are, binaries which are going around each other. So these binary stars produce light curves like this. So this is apparent magnitude. So normally all stars are stable, but now we study their surface astroseismology using their small vibrations, small minor, very small millimagnitude variations. But these variations are larger in magnitude, so you can the Cepheid variability is quite large, and Array variability is not so large. Um, so these magnitudes also depend upon the different sizes of these eclipsing binaries, and they help to understand the structure of these stars and properties. And a lot of stellar evolution, which I didn't want to cover, is also understood from studying star clusters, and which has been one of my topics. And I have used star clusters for various types of studies, including structure of galaxies as such. So if you look at a star cluster, which is basically a globular cluster, this is a low mass star. So you actually can trace all the evolutionary sequences out here. A main sequence, subgiant branch, as I said, the red giant is this, and then the horizontal branch, but subgiant is also well populated for low mass stars. So all these evolutionary sequences, this is also HR diagram. Now, HR diagram is actually used to identify the sequences, the evolutionary sequences, connection between them, and understand their properties. So I stop here, and I look forward to questions.
Thank you, Professor, wonderful testimony. So, I will ask if any members of the audience have any questions. Please raise your hand, or you can type in the chat box as well. Any questions?
I think it is a good sleep for people who, after porcelain sleep, is it? Nobody seems to have any questions.
It was a very comprehensive overview of the entire solar life cycle. So I think you're very interested, but
Yeah, please come forward and ask. You're not expected to know anything. So
Yeah.
you should be you shouldn't find issues with. Yeah, there's one goes. Yeah. How do we take care of the Doppler shifts in spectroscopic observations? Yep. Okay. The Doppler shift, I don't know whether I'll just want to explain what the question means and then I'll explain it. So I have fortunately a slide with the spectrum, right? So this is the spectral line, right? So we identify these lines as hydrogen lines. So this is like this is like an H beta, H gamma, H delta, etc. So now, if the star is coming towards us, then it will be the thing will be blue shifted. The spectral line will slightly
Line
change
was
from
like
here, or if it is red shifted, it will slightly change over here. So the central, it is the you don't have to take care of the Doppler shift. In actual measurements of velocity, you have to take care of Earth going around the sun. So that velocity you have to take care of. But apart from that, with respect to the sun, once you have a heliocentric velocity, then you measure this central wavelength and find out how much it is shifted, and that helps you to find out the radial velocity of the star. So whether the star is moving away from you and coming from towards you. So one important thing which I didn't mention was that it's very important for us to understand the motion space velocity of stars. Understanding the space velocity of stars is very important because that tells us how what is the dynamics of the things around us, what is the dynamics of the galaxy, what is the mass within. So all these are coming from the space velocity of stars that we measure, even for expansion, right? The expansion of nearby galaxies or within a cluster. What is the velocity width of the line, which is basically the velocity dispersion. So that tells you the various properties. So velocity is one important thing, and that is how we measure. So the line shift with respect to the central wavelength is measured, and that gives us the velocity. Okay. Next one, what is the reason behind the generation of energy in white dwarfs, as white dwarfs are remnant of death star or late stages of stars evolution? There's no there is no generation of energy in white dwarfs. White dwarfs therefore cool down very fast. So their cooling time is measured, and that is an important factor in understanding the white dwarfs. They don't generate any energy. They stay there because they are degenerate. They cannot collapse, but they cannot generate energy also. I hope it explains. The dwarf and giant star wasn't the main sequence. Dwarf is the main sequence. So sorry for using different acronyms. Dwarf is basically the smallest star, but not like the white dwarf. But then dwarfs in general, if you call, they are main sequence stars. Sun is a dwarf star, and giants was some main sequence once upon a time. Yes. So it was a dwarf before becoming a giant. Yes. Which chemical elements are present in black hole core? I have no idea. I'm sorry. Absolutely sorry. I don't think anyone knows that. So it's difficult. So we knew what was the chemistry of the surface of the star, or if it's still a black hole, which could have created a black hole. But I don't know that answer to that question. Yeah, what do we infer from H1 line? Okay. I did not talk about H1 line. I don't know whether anybody else is going to talk about H1 line in this winter school. H1 line is, Manolita, is anyone talking on H1 line in this school?
I think there are some lectures on
Galaxy.
cosmology and yeah, radio astronomy. So there
Okay,
maybe
maybe they
definitely they
can
could
answer there
mention
because
that.
if I go into interstellar medium and understanding hydrogen, atomic hydrogen, etc., it's not a very simple answer to give, and I didn't cover that particular aspect of.
Yeah, I think there was a lecture yesterday on ISS, but
Okay,
I'm not completely sure whether it was the case or that or not.
yeah. So there's a lot of things we infer from H1. Yeah, please ask in that thing. Yeah. Why pulsating variables has a variable luminosity? What happens actually in the structure of such stars? Okay, that's a very intriguing question. If I have time, I can take a few minutes to answer that question. I had a few slides. I removed them because I thought it'll be too much, too heavy to speak. So this is basically the thing. So you can see that this is the instability strip. It's more or less vertical in, though it's not quite vertical, but in temperature, but it spans a large range in luminosity. and this is called the instability strip. It's called instability strip because any star passing through this particular region of the HR diagram uh, has a physical possibility of according to physics, there's a possibility that it becomes a pulsating star. Now, what actually happens? So the question. It is a variable luminosity. Basically, what happens is the star basically shrinks and expands and shrinks and expands. So the temperature and luminosity acts in such a way that there is a light variation, and it is more like a sawtooth variation. It's not like an eclipsing star where there is a symmetric light curve. The increasing and the decreasing light is not symmetric. The increase goes very high and then slowly decreases, increases, decreases, sawtooth. So there is an increment in the luminosity because the radius changes and the temperature also is changing. What happens actually in the internal structure of the star? So what happens is it's actually a sink. Basically, if you, let's say the star is small, and then it starts to pulsate. So when it contracts, the internal heats up, right? So that heating is used for changing the one of the ionization states from neutral to ionized. So when that ionization happens, the heat increases, but that it is not trying to, it acts like a sink. So once it completely ionized, it becomes opaque when it is going down. Then once actually the completely ionized, it becomes it actually can conduct conduct the energy from inside to the other, the photons, hydrogen photons. So then it actually lifts up. So when that happens, the energy, the luminosity increases. Again, it slowly builds up because the ionization state, it is actually using the energy to ionize. It's when it is fully bloated, the ionize becomes neutral, and then again it becomes completely ionized. Then again blows up. So this is a cycle, which the layer of this ionization front is different in different types of stars. So these are Cepheids, and these are Rayleigh variables. And different temperatures are involved here. So different types of species are also involved in the ionization here. So it is not very simple mechanism, but this is very well understood. And these are in fact standard candles. Cepheids are in fact standard candles, and Rayleigh stars also, to understand the distances. Because though they are variables, it's actually counterintuitive, but variable stars help us to, we know the period. Once we know the period, we'll know the luminosity. So once we know the luminosity, we can actually compare the measured apparent magnitude, whatever we have measured, to the absolute, what is expected. That difference gives you the distance. So these are very important stars in standard candles, and a lot of research goes on in it. um, why do only sun-like stars have convective envelopes and radiative cores? Okay, that's a very good question. There is a fundamental nature there. One is that the sun-like stars, the kind of reaction, like if you say that the sun has 1,000,000 degree Kelvin in this in the core, is it enough to fuse hydrogen to helium? No, it is not. But due to quantum mechanics, we understand that there is a non-zero probability of hydrogen, the protons combining to become helium. So the reaction, therefore it is happening, but the reaction rate is very, very low. And the kind of it's a pp chain, the proton proton chain is happening there, very low reaction rate. So the energy production is very low and sustained for a very long time, and therefore you don't have a buildup of a lot of at high temperature here, and then the energy has to be transported. So the heat and the temperature gradient is not so high within the stellar core. So the relative temperature transport is enough. But on the other hand, the outer envelope is not able to take that up. So that becomes convective. So inside is radiative and outside is convective. That is sun. But when the star mass is between around 1.2 to 1.3 solar mass, the pp chain, the interior temperature goes higher, and there is a transition from pp chain to CNO cycle. Now, CNO cycle is very highly temperature dependent. The temperature, the dependency of, I think, 6 power, 8 power or something. I can't quite remember. But then the point is that the temperature, the reaction starts and the temperature goes very high, such that there is a huge temperature gradient within the core itself. And the energy transport is not able to happen in radiative mode. So it becomes convective. Now, once that becomes convective, when the energy production is able to make the surface of the inner core, outside of the core, to higher temperature, the outside layer need not be convective, it becomes radiative. So stars which are more massive than 1.2 solar mass will have a convective core and a radiative envelope, but stars with mass less than 1.2 will have a radiative core and a convective envelope. Um, what is the reason for the star being huge?
I think that is related to the giant stars.
I'm not quite able to understand what it means. What the question is. Sorry.
Gauri Shankar, can you please clarify what exactly the question? Okay,
Giant. Okay, giant
giant
stars.
stars.
Giant stars. So in the let me go to an HR diagram. Yeah, okay, this is fine. You able to see my screen now? Yeah. So what happens is you can see the radii, right? So radius is increasing. So what actually happens, there is a limit here beyond which if you keep expanding, it cannot cool down. So you have to you have to spend more energy to cool down. So in which case it doesn't have any more energy to cool down. So what happens is it starts increasing the luminosity. So as I said, it's a thing between the radius and um, mm, the temperature and the luminosity happens, right? So once it starts increasing, the radius starts increasing and the temperature cools down. But beyond a certain stage, it is not able to push up. So the inner core, there is a rearrangement that the inner core is contracting, but the outer layer, the hydrogen shell burning, basically actually switches off for a little while and then starts again. And in that process, it's able to just sustain that particular size, but it slowly expands in the radius, but its luminosity increases. So the temperature becomes more or less a constant. So in the equation sigma t raised to 4 pi r square, r increases, temperature remains a constant, and the size increases as a function of the luminosity increases. So it's a radius effect, and it cannot cool down anymore. So it has limit to its cooling, so that the temperature in general becomes a constant. So whatever is it is expanding, it is the temperature which is being the energy which is being produced, extra temperature is used to expand. So it is actually expanding without increasing the temperature. So that is why it becomes a giant. I don't know whether is clear. Okay, so I don't know how many more minutes I have for
Yeah, we
questions.
have
Just
I think 5 more minutes we can have. So
okay. Okay, so the
there is
next,
one more question.
yeah, yeah.
So,
So why supernovae 1A happens with stars evolving with a neutron star, which is grabbing the radiation material from that star. Um, 1A is not with supernovae. Sorry, 1A is not with neutron star. So type 2 supernovae are when you have a high mass supernovae. I'm not an expert in supernovae, but there are a lot of sub-classification within supernovae. But then in general, the major two classifications are type 2 supernovae, where you have high mass stars which are ending their lives. And the end product can be a neutron star or a black hole. So that is the end product of a type 2 supernovae. But type 1 supernovae is coming from a wide dwarf in a binary system. So the white dwarf basically is less than 1.4 solar mass, and it is actually tries to gain mass in a binary system. It accretes mass from another star, and then the thermonuclear reactions in certain cases, like in the recurrent novae, it just keeps in classical novae it completely ejects out, but in recurrent novae slowly it increases its mass, and when it actually reaches beyond that state, it collapses, and in that collapse a lot of thermonuclear reactions happen, and material is released. So that is type 1a supernovae.
any other questions?
Okay, is gravity applies on light? If it does, when? Why? It what do you mean? Applies on light.
Um,
Applies on light is not very clear.
yeah.
Yeah, next one is, can neutron stars further become black holes? Um, I don't know. I'm not an expert. Probably Manonita can explain. But
Yeah, in
I
various
don't know.
spatial circumstances,
Yeah,
like
okay.
the
Yeah,
recent neutron star merger, which
yeah.
is expected to give a black hole. Yeah.
Yeah, we know the bending of light, right? So it does affect. So we know that there is a, we have seen the, experimentally, we have seen the light bending, right? So,
Yeah, the the question is not very clear. Maybe Hariom can clarify your question because from here it's difficult to answer
yeah.
what exactly is the question.
Any more
Hello.
questions?
Yes. Yes, go ahead.
Yeah.
Hariom, please go ahead.
मैम हिंदी में बोल सकते हैं हिंदी में
I'm not very comfortable. I'm sorry. I can
मैम
understand,
ग्रेविटी
but not much.
मैम ग्रेविटी मतलब ग्रेविटी लगती है लाइट पर
Yeah, yeah, that is what we observe, right? We do see.
Yeah, I think the question is answered as Professor Subramaniam said just a couple of minutes back that light bending is observed. So if there are any other questions, we can answer them. And there is something I would like to ask is
Yeah, sure, sure. Let's go.
you mentioned this seismology of the stars. So
Yeah.
what kind of information one can extract from studying the seismological properties of stars in general?
Okay. So, when you have, okay, even this is here itself, this is a good thing to start with. So, depending upon the surface parameters, the density and, yeah, I think probably the density, you can actually see what types of waves can propagate and what kind of vibrations are possible, like in the case of seismology. So the small variations which we can see in Kepler data, which is basically the fast photometry. So you can see millimagnitude variability, small variabilities, and their frequencies can be estimated. And these frequencies help in identifying whether the models tell us whether um, um, these kind of frequencies are allowed for what types of stars. So we, by looking at the frequency, people have seen whether, in, let's say, in these kind of diagrams where you can see that this particular this is the helium main sequence, is a red clump, okay, and this is a red giant, right? So it's very close. Observationally, in general, this falls very, very close together. So if you measure, if you look at these kind of stars and you want to separate them, whether is it coming from red giant branch or it is actually coming from horizontal branch, the frequencies can actually separate. So basically, the frequencies can separate out and tell you which are the evolutionary phases stars are. If there is any, um, um, uh, you're not able to separate them. So if there are two, three things mixed together, what type of stars these are, these the frequencies can tell you. So Kepler has been able to do this. But you need to have good signal to noise, fast cadence photometry.
Okay, thanks. Any other questions from the students?
No.
There's one last question. Maybe we can take this and end with that. What detection method is used to detect the presence of exoplanets around pulsating variables?
Yeah, so exoplanet light curves, as I said, is like a I don't have the light curves. I actually deleted those slides because I thought it will be not possible. So the pulsating light curves we know very well because they are asymmetric curves. It's like a sawtooth. It goes like this, comes down, goes like this, comes down. Okay, and the exoplanet light curves are also very well defined. It will just have a dip, go down, and goes like this. So it's likely a dip, and then as the depending upon how long the a transit happens, the transit light curves are very clearly known. So if you're looking at transit light curves, then it will be superimposed on the pulsation light curves. But remember, the exoplanet, transit light curves are of the order of millimagnitude. So it's very, very, very fine photometry is needed. Light curves for pulsating stars need not be at this level. But since these two have exactly very well known signatures with repeat at each intervals, you can actually differentiate it separately. And that is the reason why we have even a star with multiple planets, we can differentiate. It's the same way. Because you can repeatability, you have to have, and then subtract that component, and then you can actually, whatever is left over, you can fit with the rest. So it is possible if it is a transit light curves. If you're looking at velocity patterns, even there wobbling is there. So you have to have a different types of wobbling. And then the pulsation also velocity changes. But once you model it out, you should be able to fit in both the components. Hello? Am I audible? Hello?
Yes, your voice is coming, ma'am.
Okay. All right. So, Manita, can we close this session?
Yes, I think there are no more questions.
I think now we may close the session and continue for next lecture.
Yeah. Okay. Yeah. Thank you.
Thanks a lot.
Yeah.
So Sanjay Gupta ji, please may continue.
Yeah, Professor Parihar has joined.
Yeah. All right. I'll quit now. Yeah.
Okay.
Hello. Hello. Professor Parihar.
Sanjay ji, yes, I'm there.
Yeah, you
Okay.
can just your question, sir.
All right.
Before we start.
Okay. Start share. Okay.
Yes, sir. It is visible. You can change a bit, like 1 or 2 slides. You can change over. Yeah, this is visible.
Then we can.
Yeah. Are you ready, sir?
Actually, link is not very good, so I will go with our. Sorry, not with video, only audio. So you can't see me. You can hear me very well.
And the slides are visible, so I think it is going to be.
Check with the part.
Hello, everyone. Are you able to see the presentation, please?
Yes, sir.
Yeah. Shall we start now?
Yes, sir.
Okay. So, a very good afternoon to everyone. In this second session of the day 3 Winter School of in Observational Astronomy, we have Professor Padmakar Singh Parihar with us. He is professor in Indian Institute of Astrophysics, Bangalore. Professor Parihar doesn't need any introduction as such, as his work is very tangible and it speaks a lot about him. But still, let me attempt to show a candle to the sun, what is usually said. Professor Parihar is a jewel carved in Pandit Ravishankar Shukla University, Raipur. Erstwhile, it was in Madhya Pradesh, so we are proud to say that, okay, he is a product of Madhya Pradesh also. He completed his thesis 2 decades ago in photometric study of binary stars. He has more than 50 research papers to his credit. Professor Parihar carries specific interest in exploring star formation and young stellar objects. Not only in deep space, he is equally interested in young enthusiasts of astronomy on this planet as well, and has guided several research scholars so far. Professor Parihar is deeply involved in astronomical instrumentation. He has laid his hands on 2-meter HCT in the start of his career in IIA, and now he is active member of the Indian Core Committee for the 30-meter telescope project. He heads the technical council of Dongla Observatory, and it was his dedicated effort that gave shape to this observatory with many promising features for all of you. He is also working to develop large optical segmented mirror for our country. With this short gloss, I invite Professor Parihar to enlighten us on today's topic, optical astronomy. Professor Parihar, please.
Thank you, Sanjay ji. I think you have glorified too much about me. I am very ordinary person, but I have very keen interest in building a telescope as well as the facility. So last 10 years or so have gone in doing the same work. So I'm not doing much science these days, but just thinking about telescopes and trying to make one after other small to big telescopes. So this is very interesting field to me. I hope that participants will enjoy my presentation. So it is a little lengthy. I think I have around 40 to 45 slides in a 45 minutes time, but I may require a little more time. So let's see. Trying to talk like this. First, I will be talking about optical telescopes. I will try to get a little bit technical information about the telescopes. Telescope. I will be not talking about other telescopes. Telescopes are very different kinds, and the optical is though it is classical, but it becoming lesser and lesser important field than the other fields. Okay, beautiful observatories in the world as well as in India. I will show you beautiful pictures of these observatories, and including few videos so that you can have some feel for these observatories. But while sitting in a village, it's very difficult. Now I'm in my village, Chhattisgarh, and sitting from village is really tough. How long I will be lying? Okay, so let's hope that there will be no internet problem. And then talk about observatories in India. We have many observatories located at different part of India, and then very important tool which can be considered part of the telescope is use of active and adaptive optics. So by using active and adaptive optics, we can make our telescope like a space telescope. It means I will explain that later. So slides which you might have seen many times, or you will be seeing many times. The slide atmospheric transparency. As I said in the beginning, though astronomy started with optical telescope, but now we have telescopes starting from radio, infrared, visible, ultraviolet, X-ray, and gamma ray also. Because the cosmic object emits radiation of all kinds. So to get much more deeper information about these all kind of telescopes, and all these cannot be actually placed in the ground because we have atmosphere. The atmosphere which is surrounding us absorbs many different part of the spectrum, electromagnetic spectrum. So part middle, you can see cartoon. You can see where we have visible window in optical, which is shown in rainbow kind of colors. Then you have some in the infrared, near infrared, rest of entire band is blocked by atmosphere, so we can't see object while sitting on the ground in infrared, X-ray, in infrared, in high energy. So only in radio, in optical, as well as partially we can see the object. And the bottom one is the object, a beautiful galaxy, which is shown in a different wavelength band, starting from radio to infrared to visible to ultraviolet to X-ray. So to get comprehensive understanding of the object, we have to have all these kind of telescopes. So I will be talking about optical telescope only. The optical telescope, as I said, it is a classical one. So first telescope which was not invented but used by Galileo is so right, it's here, and that was like a toy kind of telescope. But using such a small telescope, it was Galileo who could make many discoveries of very important, very important discoveries. Solarized the science. Like the one is like knowing the Jupiter has got this moon. Philosophical consequence. I don't want to go to those history, but knowing that there are objects which moves to importance. Otherwise, before that, The classical notion was that all objects move around Earth, but Galileo, who used this kind of small telescope, pointed it to Jupiter, Jupiter's 4 Galilean moons, which were revolving around the Jupiter. Imagine how small telescope he used and discovered such an important thing. Who is my also thesis supervisor, has talked a lot of things about all these observatories from mid modern. So I will not spend too much time. Slide a few examples. The central one is a telescope built by William Herschel. William Herschel and his sister Caroline Herschel, they made many telescopes of different size, and in 17th century or century they could build a 1 meter size telescope, and this is one example. They used to make a big telescope with large structures, and working this telescope in very dark night with his sister around was really very difficult task. Not difficult, but they have made many discoveries. So I don't want to go to history, but the center one is a historical telescope built by William Herschel. Now, 1 meter, 2 meter, 3 meters. The world has moved very far. Having access to largest telescope like 40 meter size. And when it's a 40 meter size, then I will explain what we mean by 40 meter size. It is not the structure is 40 meter. The mirror which the light from any cosmic object is 40 meter, and 40 meters is like a small football ground. So 40 meter size telescope, and this is the ELT, extremely large European telescope. The bottom graph shows how telescope has evolved over the period, starting from Galileo, who used telescope to now, and when is a new technology. You can see the jump in size, and it is not linear, but it's logarithmic, and many building ELT and TMT is not happening in time. Similarly, when Herschel built telescope, it was not he could make what others were making by using innovative technology. So you can see this is graph shows how telescope size has increased over the period. Very basic. What is a telescope? And when you say telescope, you may be thinking about this. I hope a small handy unit which is a little larger than binocular, hold in hand and watch through. So telescopes are made by using two different approach. The one is using lenses, and that is very using lens, like Galileo telescope or lens-based telescope. A large objective lens at the entrance. The point will be somewhere in between, where the light will converge and form the image. And again it diverges, and there will be eyepiece which makes light parallel. So light comes from distant object is a parallel light, a beam. Light goes after the eyepiece is also parallel light beam. And then I receive this parallel light beam, and using its internal lens, it forms image on the retina. So this is classical refractive telescope. Use the lens, but instead of lens, it uses. So unlike lens which sits at the front, the mirror which collect the light will be on the back side. So this is the mirror, the primary, we say primary mirror. A light will fall primary mirror, then it will reflect back, and mirror, and we have eyepiece here. So without using the lens, we can use mirror and get the image or from the objects. So this is a reflecting telescope. And the idea of building reflecting the telescope using the mirror is not new. It was Newton who made world first reflecting telescope. Okay. Kind of telescope. One thing before I go to different kind of telescope, you please keep in mind, bear in mind that when you talk about larger and larger size telescope, that time either we'll be talking about this lens which is no more in use, we'll be talking about primary mirror. So once we said 5 meter, 2 meter, 10 meter, 30 meter, 40 meters, I'll be talking about this mirror, which can be single monolithic mirror or second. I believe all of you comes from science stream. You may be knowing much more about optics than what I learned. So this is very basic. For the telescope, we need at least 2 mirrors. There can be more than 2 mirrors. One is the primary mirror and other can be secondary mirror. And these are different possibilities of how we can arrange these 2 mirrors and get the telescope. And these telescopes will have different kind of the quality. Okay, right. So the first one is called a Gregorian telescope, which will have parabolic primary mirror. The mirror will be parabola is a ellipsoid, and it is the ellipsoid is placed after the focus of the primary mirror. So this is focal point of the primary mirror, which is paraboloid, and this is secondary. And secondary is ellipsoid and concave. So both are concave, and making concave mirror as a secondary is easier than making convex mirror is required in this case. So this is a Cassegrain telescope, classical Cassegrain telescope. It uses parabola like is Gregorian, but secondary is the point of the primary. So that's why it requires a convex mirror which will diverge the beam and then beam will be focused over here. Okay, so this is Gregorian, this is Cassegrain, and then the most popular optical configuration used for building telescope is Ritchie-Chrétien, and here the primary will be hyperbola, second hyperbola, primary is concave, secondary is convex, and you can see focal point here it is for in the back side, but there can be many focal points which I will show you in the other slides. Using elliptical primary and spherical secondary, and this is called like these are just few examples. You can have many different configurations, many different kind of telescopes optics we build based on the requirement. Some of them will be used to have higher magnification, some of them can be used to see larger field of view, some of them can be used to put instrument at the right place. So they have different advantages or disadvantages too. Okay, and this is about telescope. I will not talk much about this. Like any optical instrument, telescope also goes through the aberrations. And these are well-known aberrations like spherical aberrations, coma, astigmatism, field curvature, distortion. These are the important low-order aberrations which need to be minimized when we are designing a telescope. These are different focus, as I mentioned.
Sorry to interfere, sir. Your screen is stuck at a particular slide. I think it's slide 2 only.
What happened?
Sir, your
Can you
screen is
repeat, please?
stuck. The presentation is not visible to us, sir.
What you see now?
Yes, sir. Now we see telescope configuration focus.
This one is the correct one, right? I'm here only. Shall I move?
So past two slides wasn't visible for all of us.
Let us not bother too much about missed slide. You have heard Meena, that's okay. Can you see this slide?
Yes, sir, sure.
Okay, move on. Okay. Uh, this slides talk about the focal point which we can have for any telescope. The one focal point can be prime focus. So if you have just a single mirror, primary, then image can be formed at the prime focus with use of some correcting lenses. Okay, and prime focus usually gives very wide field, like 1 degree, 2 degree, 3 degree field is possible by using prime focus with some correcting lenses. The other focus option is the Cassegrain focus, which will be back. The focal point will be back of the primary mirror, and this is very widely used. Focal is plane, and very huge, big instruments are mounted on the back of the telescope. Okay. Another option is if we bend light at 90 degree from the optical direction, then this focal option is called Nasimet focus. And again, it can host huge instrument, like a 10-meter telescope can host 20-meter size, 20-ton size heavy instrument. So 20 ton is like a truck loaded with, will be sitting on the focal plane. I will show you one of the pictures of such instruments. Other focus is focus. In this case, light goes through many reflections, and finally it converges to the point where you'll be having largest focal length. Largest focal length also facilitate very high spatial resolution, which I will be discussing later. It is about resolution, right? So when you talk about telescope, I think the next slides are on this only. So maybe we can go to next, but the characteristic of any telescope is resolution. So why we need a telescope? So the first requirement is we want to see the faint object, or the object which is very far in sky, right? So for that we need a telescope and larger telescope. Important parameter of a telescope is resolution. How good resolution is, how close the objects are very close, like this, or some features in the extended source like galaxy or planet. So how well we can resolve too close by object or too close by feature is also by telescope size. Having telescope size alone is not enough, and we have to do something more. Okay, but telescope size decide one, how faint we can see, as well as how well we can resolve too close. And the resolution of the telescope is nicely described by this small simple formula. Okay, delta theta equal to 1.22 lambda by d. Here lambda is the wavelength, d is the diameter of the telescope, and theta is angular. slightly better the resolution, or the smaller the lambda, better the resolution, the smaller theta. So this is really, so there are different aspects of collecting power, and it depends on d square. D is the diameter of the telescope. So larger the diameter, more the collecting area, and more distant object we can see, or more faint object we can see if we have large telescope. The other is the telescope. Sensitivity of the telescope is decided by d to the power 4, where d is the diameter and 4 is the power, right? So sensitivity is how sensitive our telescope is to see or sense any object, right? And decided by not just d square but d to the power 4. And the other factors which comes here, which require little explanation. I don't want to go on that detail. Okay, then other is Stern ratio. There is a full width half maxima. The full width half maxima. If you have star, and if you see how intensity is distributed, then it will be like a Gaussian profile, and the half width, full width at maxima is a one indicator to know how good telescope resolution is, or how good the seeing is, the sight is. Those things probably I will discuss later. Okay. Telescopes are there are kind of telescope mount structure, and here I have just mentioned 2 or 3. The one mount is called equatorial, because you will be seeing that when I talk about existing telescope. So you can see different kind of telescope with different mechanical configurations. So for that, if you have some idea or different kind of mounts we have, you can get some feel what these telescopes are. So the one telescope is called, in this case, actually to point telescope to any object, you have to rotate the tube to angular direction. 2 directions are required. Then only you can locate your tube or the telescope to any object. And these 2 angles can be arranged in different manners. The one arrangement is, in this case, equatorial telescope. So one axis is pointed toward the polar axis, polar direction, and this is one rotation axis, which is called RA axis, and there will be declination axis, which the RA axis east-west, and the declination axis is north-south. So by moving telescope in east-west as well as north-south, we can point our telescope to any object, and this is real mount. The other is ultra-azimuth mount, in which case telescope moves in as well as up and down. The difference between these two, one major difference between these 2 telescopes is this telescope can track any object by moving only in one axis, but other telescope requires to be moved very, very precisely in 2 axes. Okay, so these 2 mounts are very popular, but other mounts like alt mount, hexapod mount, fixed altitude mount, and so on. Okay, these are a few examples. Okay, just now I discussed. So this is 1.2 meter telescope. This was made by ISRO long back in late 80s, and it is the equatorial telescope. So this 4 what you can see is pointing toward pole star, and the tube in the around another next. So this is equatorial telescope. The telescope is a telescope. So the whole base, this base rotates, which is called azimuth axis. This axis is called elevation axis. Telescope can go up and down. So these 2 are example of equatorial telescope as well as telescope. Very small handy telescope you can carry from one place to other place. Scope, you can't imagine how big it can be, right? And how bulky. So one example is just 3D model of one of the telescope GTC. So the moving mass, just moving, not the entire mass, the mass which will move here and there when telescope is pointed to any object will be 200 to 300 tons, and will be made of many different engineering field, right? So it requires many different discipline engineers, scientists like opticians are required, mechanic engineers required, electronics engineer, control software. So to build at least 50 to 100 people have to work over 8 to 10 years. Then only a large telescope can be realized. And money like 1,000 crore to 3,000 crores. Which is presently installed in many places around the world and functioning they are serving. So many discoveries, what you can read in newspapers, what you can see in televisions are happening by some of telescopes, right? So this I'm just giving an example of these large telescopes. The one is Gemini here, which is 8.1 meter. This is mainly American telescope. Subaru is Japanese telescope, which is actually of 8.2 meter size. These two telescopes are installed in Hawaii Island. This kick one and kick two again at Hawaii Island, but this is not a conventional telescope. I will talk about more about this kick later. This is the which 3D model I just showed to you. GTC is in Canary Island. Is very unique binocular LBT, large binocular telescope. On single mount, they have placed two huge telescopes. Each telescope is 8.4 meter in size, and they are separated with I think 24 meters apart, and that's why high resolution as well as it has more light collecting power. So it's again in America, Graham, somewhere in Arizona. This is a 8 meter size telescopes placed at the same place through interferometry. Here also in LBT, light can be the light collected by these large mirror can be combined through interferometry, and an extremely high resolution can be achieved. Same thing can be done here by combining light which is collected by these telescope to one place, so that the effective resolution can be high. It's called optical interferometry. You can see how big a telescope mirror can be, right? So this is one example of LBT mirror, which was made roughly 15 years back in Tucson, Arizona. And this is one occasion when people came, and maybe some symposium, some conference might have happened. So this is just blank. This is the middle, which was made for developing a very specialized technique. There is a very nice video. If you visit to their website, then you can see the video how they made this blank mirror blank, which is 0.4 meter in diameter. From this point to other point is 8.4 meter, and there is hole at the center. Many years to grind and polish so that like a mirror. A mirror is 8.4 meters, it's a very huge mirror. But while making the shape of hyperbola or parabola, whatever is required, the accuracy of few nanometers. So size is such a big, but the shape of this mirror should be precisely made with few nanometer accuracy so that image quality will be the one which they want, right? As is specified. If there will be departure more than 20, 30, 40 nanometer, which is very small quantity, I don't know how to explain what is. I think many of you know what is nanometer. Right? So then nano science is there, so you know the size of the nano. So here any departure in the shape by more than 20, 30 nanometer is not permitted. And imagine how difficult this task is. And not you have to only make the mirror, you have to put into the structure, and then the telescope will move here and there and maintain. So this is one mirror which is the same mirror after so that you can see the reflections. Using a single large mirror is a very difficult task, and it has reached to the limit. Now, by using any technology, it is very difficult to build a telescope which can be more than 8 meters in size. But the need is never ending, right? Always there is quest to go deeper, observe fainter object, search for very exotic object in the sky, and even search for life in the universe, right? And for all these purposes, we need a larger and larger telescope. And how to build a large telescope? Because 8 meter is almost the limit. After 8 meter, we can't use a single mirror to make a telescope. 80s, late 80s, Jerry Nelson from US, California University, who came with the idea to use smaller mirrors and put mirrors and make them such a way that they act like a single monolithic mirror. So this is one actually model of the Keck telescope by Jerry Nelson team, and they started working on this telescope project in 80, and they could complete the first telescope, the Keck telescope, in 1993, which is now world's best telescope. To have a closer look of these mirrors, then this is the one which we are planning. And this is another telescope which again uses mirrors. These two telescopes are different kind. I don't want to go details about these telescopes, but they are slightly different, though they are segmented. And this is the primary mirror of a large 30 meter. So here it requires 452 mirrors, and each mirror 1.4 meters. So you can imagine how many need and how difficult it is to put them so that it will act like 30-meter size telescope. But technology has actually matured enough now, and one can think of making a telescope by using small mirrors up to 50 meters or even 100 meters. So the largest is going to be 40 meters. So this is the solid model of Keck telescope, which is both telescopes are close by and are unique, identical, and in between you have many other facilities. In this Keck telescope, the light which is collected from Keck 1 and Keck 2 can be combined through interferometry, and so that can be achieved. The observatory, the Keck Observatory in Hawaii. 130-meter telescope, which is called TMT, and 5 countries together are actually joined and built. 5 countries are like America, Canada, Japan, China, and India. All are partners, and all we together building this telescope. The telescope is actually going through the construction phase, and to be completed. So this is the year. How much time?
Sir, hello.
How?
We have 15 minutes at least for the lecture, and then further 15 minutes.
I will try to finish in 20 minutes. Okay. So this is another mega telescope, which is called ELT, and it is roughly 40 meters in size. You can just compare the size of the telescope with these cars, which are looking like an insect, right? Telescope expensive and very complex instruments. And this is one example of an instrument which is installed in a telescope. It is called DEMOS, and a powerful instrument. Many has been done using by this instrument, and it's expensive. I will not talk more about the instrument. Ram Prakash from Ayuka is our instrument, so he will be talking about the instrument. So I just give one example, and this instrument can be 10 to 15 to 20 ton in weight and size. You can imagine, right? So this one person, which is maybe 1.5 meter, is standing in front of the instrument. There are solar telescopes. I have described as about nighttime telescope, which is used for stars and other objects. We have only one object, which is sun, which is our nearest neighbor, and it requires slightly different telescope than the one which is used at night. And these are the few telescopes which we have in India for the solar study. So this is a telescope in Kodaikanal. This telescope is within the lake. It's in Udaipur, I think Fateh Sagar Lake. Solar telescopes are in the lake or near the lake because it gives me good image quality. This is another small telescope in the same lake, and this one is the proposed India's proposed large national telescope. It's called NLST. The project is actually proven. Largest telescope in India, and size will be 2 meters. These are another few example telescope in the world. So one is Gregor telescope in Canary, and then this one is Chinese 1.5 meter telescope, and the world largest telescope was going to be 4 meter telescope. Okay. These are just for slides. I will not talk much about these slides, so you can just watch these slides and enjoy. Okay. So, observatories in the world. So these are the places where you can find big telescope, and these places are identified after a very extensive survey. So sites, astronomical sites are usually in mountain top. Have to have less number of dark nights, cloud-free nights. The atmosphere should be quiet. It should not be turbulent. Any light pollution, and the water precipitable water content should be low as possible. And the many four are important parameters. Considering these four parameters, many good sites have been identified across the globe, and few are in America. Many of them are in Chile, which is in this is one of the best site in the world. Then one observatory is in Hawaii. It has many telescopes installed by different countries, and 30-meter telescope may come over here. Then one is Canary, the GTC, what I talked about is here, 10 meters. South Africa has another big telescope. Russia has got a 6-meter telescope over here. In India, a very good site, and we have a telescope. And Australia has telescopes. So these are the places where sites are good and large telescopes are installed. So just enjoy these slides, which are panoramic view of the observatory. So this is the Keck Hawaii. So you can see these Keck telescopes and the Gemini, Subaru, and so on. And this is a 1 millimeter telescope. So it hosts many observatories. This is in South Africa. The SALT telescope is seen here, and many smaller telescopes scattered here and there. This is a very world famous Mount Palomar Observatory in California. Is named Hell Telescope because George Hell is the one who started this project. And George Hell, Jerry Nelson, and Benny Bottom. They have devoted their entire to building telescope one after others. So I don't want to go to a story, but it's very interesting story about these three great scientists, and you can say the builders of the telescope. So this is the George Hell telescope in Mount Palomar. Up to 1993, this was the world's largest telescope. Then has taken over. This Sagar, Udaipur, our own telescope. The high energy telescope, but works in optical domain and located in Ladakh, Leh Ladakh. Though you can see snow everywhere, but that is not the case. Snow is very rare. These are Indian observatories: Aries, Nainital, Kavulur, Ayuga Gravali, Ladakh. Again 2 meters, but we are aiming to have 10 meters of telescope here. Sikhar in Mount Abu. So all these observatories are a very scenic, beautiful place. You visit there, and they always actually welcome visitors as a part of outreach. This is newly added or developed telescope in Devasthal, and you can see the Himalayan range or the Himalayan range. And India's largest telescope is installed, 0.6 meter Devasthal optical telescope. Optical telescope, India's largest now. And the second 5 to 10 years time, 10 years not 5, 7 to 10 years time is NLOT, India's large 10 meter size telescope. HST optical observation can be also done from space because it has its own quality. Resolution will be extremely good. There will be no atmospheric turbulence problem, so that's why telescopes are launched in space. The this is JWST and so on. India also launched space telescope. It's a space observatory, and this AstroSat was launched in 2015, and it hosts many instruments. The one is optical UV telescope, and these are the images, and whatever images we are now getting from our own telescope is much better than any other telescope so far in UV region. So this is the galaxy image, and the down one is the image from our own Indian ultraviolet imaging telescope. Science can be done only with large telescope. That is not correct. When we are building 10, 15, 20, 30, 40 meter size telescope, do very interesting science by using a very small telescope. That's what I wanted to show in this slide. So here you can see the Gemini. This is Hawaii Gemini, 8.2 meter telescope, and public cake. And close to Gemini, these two toy kind of telescopes are installed. It's called HatNet, and this is the closer view of the HatNet. And this is same size. And a telescope of this kind, which is like a toy, has discovered extra solar planets and supernova, GRB, and many interesting can be actually discovered as well as observed using such small telescope. So one can think of using a smaller telescope. This is a small telescope what we built a long back. Now it is in different shape. It's an old image, and it is used for variability study as well as actually exploring the site. Just few slides. So telescope alone actually will not or it can't be used to have very high sensitivity so that we can see object which is very faint or very far. And the reason is these mirrors are very actually for any cheap when telescope is moving, the image quality will degrade because mirror will not maintain its shape. Change temperature, that will again deform the mirror. Very difficult to get quality image using thick mirrors, and then same time it becomes very bulky, which requires very heavy structure. In late 70s, 80s, Wilson from thinking to use small mirror, thin mirror, not small mirror. Mirror will be large, but thickness will be very thin. Mirror can be warped by some mechanism, and high quality images can be obtained. So this is called optics. Many small large telescope which has got thin mirror uses active optics. The one which we recently installed in Devastan also uses active optics. So this is the cartoon of the active optics. The primary mirror, which is very thin, and it is supported by the actuators, which can apply the force. And this is the cartoon, but the real one is here. This is 8.2 meter VLT primary mirror separate. And all the actuators, I think, actuators are located in different parts. And mirror of this kind will sit on this. And by using the force, we change the shape. How actually how much and where the shape changes are required is changed by this wavefront sensor. So there will be Sakhartman wavefront sensor, which actually knows how much actually mirror has distorted and then by applying the force, film mirror is actually deformed in such a way that it gets back its original shape. So this is called, it works in a closed loop, and it is called active primary mirror or active mirror telescope. But very fast. The correction is done just to take care of any changes due to temperature as well as not active. But the other problem of any telescope is the atmosphere. So we know all know the twinkling of stars, right? But starlight brightness changes continuously. And it's a twinkle, twinkle, little star, right? The twinkling is a problem to astronomers. We don't want the star to twinkle, okay? And but we don't have control over that because there is atmosphere, and when starlight passes through this turbulent atmosphere, then a star which is supposed to be like this get blurred, and it is very difficult to correct the blurring. So the new technology developed in late century is called adaptive optics, and the principle is simple. So this is a turbulent layer. Starlight passes the turbulent layer, and then it distorted is a plane wave. Will be a distorted wavefront, and the telescope will receive this distorted wavefront, and and some the wavefront sensor also. The wavefront sensor. With help of wavefront sensor, we can know on real time. There is a message flag. The problem of
Hello.
what shall we do? Somebody's saying that they have network problems. Shall I go ahead?
I think at least we are able to see on your slides.
Okay. Just one more slide.
Only one or two.
One more slide, then we can stop anyway.
Yeah,
okay.
This is visible, active.
Right. Somebody is saying network problem. So if it is someone's internal network problem, please keep quiet. We can't do anything unless the whole group is facing the problem. Okay. So senses any distortion in the incoming light, and then gives the feedback to a deformable small mirror, the mirror which can be deformed by having very miniature actuators, and it just deforms the mirror in opposite sense. The deformation of the mirror will be just opposite electrical conjugate. Then it becomes a plane wavefront. So this wavefront is a plane. What you can see here is a plane wavefront. This plane wavefront goes to the science instrument, and we can see very sharp, very fine image. One instrument can of one of the adaptive optics instrument, and it can be very expensive also. Sometimes it will be cost of the telescope. Which telescope is like 2 meter size telescope, then building an adaptive optic system may cost equally. And here is actually a real one also. Okay, so there is no adaptive optics working, and you can see the star will be like a blob here, and the 3D plot of the light will be like this. But once this adaptive optics loop is closed, start working, the light is concentrated, and this object becomes sharp, or star becomes very small, and the light distribution will be like, there will be many-fold improvement in the resolution as well as the sensitivity. Adaptive optics only we can think of observing any object with very high clarity. So I can show you a few examples of adaptive optics. So this is the one field where we have binary star, but we can't see any looking like one without adaptive optics. Once adaptive optics is on, then you can see these two objects. Another example is this is I think Uranus, and there's the ring of the Uranus, maybe Neptune. It's HST image from the space, and in space there is no atmospheric turbulence problem, but the same object is observed using ground-based Keck telescope with adaptive optics, and you can see how clear view lies. So one is size of the telescope is large, that's why resolution is high. The other reason is active. Even having larger telescope but no active adaptive optics, it's see high resolution clear images. This is the one example. So even now using adaptive optics, we can get very nice size images which may be equally good like a space telescope or maybe better than. I can stop here. Anyone has any questions, then I can take.
Yes, please. Questions? Any questions, please, from the participants?
Hello.
Yes, please.
Yes.
Yeah. Good evening, sir. Sir, I was wondering, is there any limitation, theoretically, is there any limitation to the size of reflector telescope that we can build? Like, there is a limitation to the size of a refractor size telescope, but in the reflector case, is there any limitation?
Okay. When you say refractor telescope, largest telescope ever made using lens is 1.1 meter Yerkes telescope. I think Hale was the one who built this telescope in early 19th century. After that, making a lens of 1 meter beyond is difficult because of the gravity and temperature. Lens will go through the distortion. Telescope is pointing here and there, and then image quality will degrade. So,
Sir, I'm asking about I'm asking about the mirror based.
the lens based is 1 meter, and that is largest. And the mirror based telescope, one can think of building up to 100 meters. There's no problem in putting mirror of any size. Have a mirror, segmented mirror telescope of any size is not a problem. The problem is once the structure becomes very large, then the wind, because you have to open the telescope to see the object. No? The dome need to be open, and once dome is open, then wind blows, and it creates many problems which is very difficult to handle. The vibrations, the wind jerk, and so on and so forth. So
Okay, sir.
Thinking to build telescope of 100 meter size, but looks like the current technology requires improvement. There are many challenges, so that's why they have limited their size up to 40 meter, right? 40 meter, 40 meter was actually little more than 42 meter, 42 meter has become 39 now. But up to the telescope is possible using mirrors, and beyond that, there are difficulties which need to be overcome.
Okay, sir. Thank you.
Any other questions?
Out.
If you type in the chat box if you have any other questions. If there are no other questions, hello, Professor Parihar. Looks like there are no other questions.
Thank you so much for giving me
Thank you.
and yeah,
That's a very exciting, wonderful talk
thank
you've
you.
given us onto the optical astronomy telescope. It was a very exciting talk. Thank you so much.
Yes, sir.
So I will just
Thank you, Pariyar sir. Thank you very much. For nice
Yeah, thank you so
lecture.
much. Yeah, yeah. Okay.
sure.
Okay.
So the next session will be on the Python documentation. So the speaking with the document itself. He's already here. So Dr. Majumdar, we can try out the slides if you want.
Okay,
That
thank
we
you.
have.
Yeah, can you hear me?
Start. Yeah, I can
Hello?
hear you loud and clear.
Oh, okay, okay,
Hello.
fine.
I can hear you loud and clear.
Okay, okay.
We can try out the slides. We'll start the session at
Acha.
5, but
Okay, fine.
we can try out the.
Okay, I actually want to share the entire screen because I will basically move back and forth between
Sure,
the
whatever you
slide
prefer.
and yeah.
Sure. Whatever you prefer.
Mm, yes. Let me check. Is it visible right now? I am my.
Yes.
Okay,
I
fine.
think yes.
If I
Yes.
change to a Python
Yeah,
notebook, is it
perfect.
visible? Okay. Okay.
Perfect.
Let me switch
Okay.
to a PDF file. It is visible, right? Right now, the PDF file
Yeah,
as well.
totally visible.
Okay,
Yeah,
fine.
visible.
So sorry. Yeah. So yeah.
Would you try?
Can you see the slides now?
Wait. Yeah, I can see the slides.
Okay, perfect. Yeah.
So your video is not visible. It's fine with me if you
Oh,
don't want
okay, okay,
to
okay.
switch it on,
I can
but
I can switch
just
it on. I can
inform me.
switch it on. Yeah. Just a second. Second. Yeah, because the positioning of the camera in my laptop is somewhat odd. That's why
I understand.
it will look weird. Yes. Yeah. Fine.
Okay, I
Okay.
think we can see you.
Hmm.
Oh,
Okay.
okay.
Fine.
Just let's wait for 5 minutes because
Mhm.
that's the scheduled
Fine.
time. Thanks.
questions.
Maybe we can start.
Okay.
So, introduce. So, welcome everyone. Good afternoon.
Hello.
Of data analysis using astrostatistics. This session will be the first part will be given by Dr. Majumdar, who is the assistant professor at Department of Astronomy, Astrophysics, and Space Engineering at IIT Indore. Dr. Majumdar's research interest concerns cosmic dawn and the epoch of reionization, 21 centimeter cosmology, square kilometer array, large scale structures, n-body simulation, statistical inference, and low frequency radio interferometry. Dr. Majumdar did his PhD in astronomy from IIT Kharagpur and master's from IIT Kharagpur as well. Right now, his interest is in primarily in cosmology, but this talk he will be giving on the topic of tools of data analysis using astrostatistics. So over to you, Dr. Majumdar.
Oh, thank you for the introduction. So I have been asked to speak about astrostatistics, but I think that's a quite vast subject, and it is difficult to, at least for me, to do justice to that subject within just 40 minutes. So I decided to speak about only one small aspect of astrostatistics, and within that particular aspect, I decided to speak about only one application, okay, that we generally use on day-to-day data analysis particularly. So I will be speaking about Bayesian inference, and more precisely about parameter estimations using Bayesian inference. So why, first of all, we need this thing, astrostatistics or Bayesian inference in general? Because most of the time, the data that we are dealing with from observation or simulation or whatever, we are dealing with, we have a general question that how do you reason in situations where it is not possible to argue with absolute certainty? So you need to provide some sort of reasoning when given the fact that you already know there are significant amount of uncertainty associated with the data that you are dealing with. And that's why the concept of probability comes into place. And from the Bayesian statistics, Bayesian point of view, the probability has a very specific definition compared to, there is another school of statistics which is called frequentists point of view. And we will stick to, there is a debate between these two schools, and we are not going to discuss that at least, and it may take a longer discussion. We will just stick to the Bayesian definition of probability for the sake of this particular talk. So why there are uncertainties in the data? You may ask that question, and the source could be many things. For example, the noise in your measurement, the intrinsic quantum randomness in the system, or effective randomness in a complex system, etc. All of them together actually contributes to this randomness or uncertainty into your data. So essentially, we always, even if there is no randomness, many a times we may have incomplete knowledge about the system. So all of this together actually contributes to the uncertainties in the data. So Probability, when we are basically the problem that we are dealing most of the time in astronomy or in cosmology is that it is called inverse problem. That is, given a certain amount of data, what can you tell about the system that has created that data? Now, when I'm saying system, that may mean some sort of physical system. So let's say there is some sort of nuclear reaction going on inside a star, and you are getting some sort of radiation from the star. So given that you have some uh, some calculated measure of the radiation that you are receiving from a star, what can you tell about the physical processes that are going inside the star? So now, to know about the physical processes that may go inside the star, you may have to come up with some model. So you may have to ask the question, okay, what is going on inside the star? I am pretty sure this has been discussed in this series of talks, and maybe there might be some sort of physical model that we can build for whatever process that is going inside the star. And now, if I, let's say, vary the parameters of this particular physical model, what kind of radiation do I expect? And given that I have received some sort of radiation, what does that tell me about the fact that I have assumed a particular model? What are the values of the parameter of that model? So how can I connect my observation finally to some sort of, let's say, understandable physical quantities? So there are three kinds of problems. In this class of inverse problems, there are three kinds of problems that generally people deal with. One is hypothesis testing, one is parameter estimation, and one is model selection. And as I had mentioned, we will just discuss parameter estimation in this talk. So far I have not spoken anything about what is probability, which is central to the idea of these uncertainties, etc., and how to deal with the uncertainties. And if I look at the probability from the Bayesian point of view, it is nothing but a degree of belief in a proposition allocated by an observer, given that whatever available information or data that the observer has, and also given that the observer has some sort of understanding or not understanding about the uncertainties that are associated with the data. Okay, so that can be the noise of your detector, that can be something else, something happening in the upper atmosphere that is changing the radiation on its way to your detector from the star, etc., etc. And this is why you need to basically define the probability. So various kinds of probability you will deal. Okay, so what is Bayesian inference? If I go to the very basic of it, it is nothing but the famous Bayes theorem. I think many of you have studied it in your high school, at least once, when you looked at the relationship between different conditional probabilities, particularly the product rule, if you remember. So it is, given the data or observation, what can we infer about the model and its parameter? That is more or less what Bayes theorem tells us in a very, very crude manner of saying. And here in Bayes theorem, we are treating the probabilities, various kinds of conditional probabilities, as the degrees of belief. And the conditional probabilities are shown here, where p of theta given the so here theta is the parameter of a given model that you have assumed to be true. We will if you do not if you are basically dealing with several models, then you are doing something called model selection. So you do not consider one model to be better than the other. What you want to try and test is that which one is the best fit. So, but we will not deal with model selection. Let us say for a given model, you believe that the model is correct. So probability of the parameter having a certain value given the observational data d is equal to probability of data given that parameter times probability of the parameter divided by probability of the data. So there are several things that are missed here, and those things are basically in all these cases, you have assumed a particular model to be true. So all of these probabilities should be read as given the model. Okay. So at the end of the day, what we will deal with, okay, so let us look at the different components of this Bayes theorem first. So on the left hand side, because we are interested at the end of the day, what is the value of the parameter or best fit parameter for a given data, right? So that is what we are interested in. So what is the probability density function for that parameter given the data? So that conditional probability density function is called posterior. On the right hand side, this particular thing, probability of the data given the theta, is called likelihood. Probability of theta is called the prior. Probability of data is called the evidence. Just to remind you, all of this has this I and M inbuilt in them, which we are not mentioning explicitly, where I is called the prior information that you already have about the data, and M is the specific model with which you are dealing with. So all of those things are also there, but we generally do not explicitly mention them. And in most of the cases, when we are dealing with a single model, and then this particular quantity, probability of data, which is popularly known as the evidence, is turns out to be a constant, proportionality constant. So we don't have to actually evaluate this quantity, and we can be basically happy with a proportionality relationship between the posterior and the likelihood and prior. So P of theta is called the prior. So at the end, what we end up dealing with is something like this. So this is kind of a reduced form of Bayes theorem for parameter estimation purposes. And more often, the prior is kind of considered in most of the simple cases of parameter estimation. Prior is considered as a kind of flat prior where all values of parameter within a range are equally probable. We'll assume them to be equally probable. So that is my starting point. So then I can forget about this P of theta. It essentially just provides a boundary within which I have to explore the parameter values. So at the end, it ends up with posterior is proportional to likelihood, that kind of relationship. So at the end, we deal with only this one. We try to evaluate only this one, P of data given the theta, the likelihood. Okay, so first of all, I have all these slides, so you can look at them later. But what I would like to focus on is how you actually evaluate this posterior or the likelihood times the prior in some way. So let's say I am dealing with two parameters. So let us assume this theta is a vector. Okay, so it has and it's a 2D vector. So what does that mean? That means that I have two, let us say, free parameters for my model. So theta 1 and theta 2. It has two components. So now I want to find out what is the most likely region in the parameter space that actually fits best to my given data. That is what I am trying to figure out. And I have to, that's why, evaluate this product of these two conditional probabilities. And as I said, the prior is most of the time is a flat prior, so I can forget about that. All I need to evaluate is this likelihood. Okay, so if I want to evaluate this likelihood, that means I have to explore this space of where these parameters are defined very meticulously, right? Because I don't know what is the distribution of this likelihood, this particular conditional probability PDF. It may be a Gaussian, it may be having multiple peaks. So it can be of any shape. I do not have any prior knowledge about that. So I need to find out an effective way to search the parameter space so that I can evaluate the likelihood values quickly enough and explore the parameter space quickly enough and efficiently enough to tell something about the parameter values or the best fit parameter values, or find out the best fit parameter values probability density function. So most often people use some sort of sampling technique for this, and probably you have heard about it. One of the most popular sampling technique is Markov chain Monte Carlo technique. And within the Markov chain Monte Carlo technique, there is something called Metropolis Hastings algorithm that people use most often. And it is one of the most simple, intuitive algorithm that you will find almost being used almost everywhere. I mean, not only in astronomy, not only in cosmology, but almost any field of life, it is being used continuously because it's very easy to implement. And today we will specifically discuss that, how we can we will take some sample data and we will try to infer the parameters for a given model from the data by writing this Metropolis Hastings Markov chain Monte Carlo algorithm. We will explore the parameter space. So I am pretty sure all of you have already seen some, let's say, some example of this particular algorithm. Maybe not this specific algorithm, but the sampling technique and the parameter estimation, application of this parameter estimation, specifically in the case of cosmic microwave background radiation. So I'm 100% sure you have heard about this particular phrase, that this is the picture of the baby universe or something like that. That is the earliest picture of the universe that you can ever take. However, even if you have taken this picture, it's all nice and beautiful. It has this nice, basically impressionist painting like features. But what does that tell you about the universe? How do you know something about the universe from this picture? So people then go ahead and from this picture, they try to calculate some sort of statistics. So some sort of measurable quantity. In this case, they try to calculate something called a power spectrum. What is a power spectrum? Power spectrum is nothing but the amplitude square of the fluctuation in a field for a given length scale. So here, let us say this is the length scale, which is plotted using angular multiples, angular multiple modes, and the y-axis actually shows you this. The top panel actually shows you the power spectrum of CMBL. And this is some sort of statistical measure of the fluctuation in the temperature field of the CMBR that we see here. So as you can see, these colors represent fluctuation. As you can see here, this blue means minus 300 millikelvin, microkelvin, to red, deep red means 300 microkelvin. So the fluctuations in the field vary between these two ends roughly. So it actually, this power spectrum actually measures these fluctuations at a different length scale. Okay, so let's say you have quantified that particular picture, you have reduced it into this particular plot. Let us say you have managed to do that. But then what next? From this particular plot, what can you tell about the universe? That should be the next question, right? So people came up with a model called lambda CDM model of the universe, which has a list of parameters, and those parameters are listed on this left-hand column. And using that power spectrum, and given this model that people believe to be probably the best representation of our universe for the time being, for given the observations, etc., people tried to estimate what are the best fit values of the parameters that I will get, given that I'm getting this picture of the baby universe, and from that picture I'm getting this power spectrum. So they use the power spectrum as a measure, a statistical measure of the fluctuation in this particular field, and using that statistical measure, they did something called parameter estimation. That is precisely what we are going to discuss today. And as you may know that the discovery of the fluctuations in the CMBR temperature has led to, I think, multiple Nobel Prizes, not one. So these are the y-axis essentially shows different parameters of this lambda CDM model of the universe, and x-axis also shows different parameters of that model. And essentially these different contours are different statistical measures, or jointly combining different statistical measures together. People have tried to constrain these parameters. So the deeper color means 1 sigma, or let's say 68% confidence interval, and the lighter color implies 95% confidence interval within which. So instead of the entire parameter space, they have managed to squeeze it. So if you look at the smallest error ellipse, they have managed to actually pinpoint the parameter values. Not necessarily pinpoint is a wrong phrase to use in this case. They have managed to constrain the parameter values to very, very finer precision, I would say. And this was not possible 10 years ago or 20 years ago. This was unimaginable. So because the quality of data, quality of observation, the amount of data has increased, that's why, and different ways of basically quantifying the observations have come up. That's why people have managed to constrain the cosmological parameters so well. That is one thing. Okay, so we will not go into this CMBR data today. So what we were discussing earlier, if you recall, we were discussing about this parameter space theta1, theta2. I am assuming there are only 2 parameters. Okay, I have to be a little faster now. So I have only 2 parameters in my model. I have some data, forget about from where the data is coming, and I have some sort of physical model that I believe explains the data. Now this physical model has 2 parameters, theta1 and theta2. And my job is now to define the likelihood for given data with these 2 parameters, and then explore the parameter space, explore the this 2D parameter space using some sort of random walking method. So sample the parameter space and evaluate the likelihood in each point of this random walk. You may ask, why should I do a random walk to start with? Good question. If you have enormous amount of computing resources, what you can do, actually, you can define very, very fine grid, uniform grids, like a graph paper. You can divide this particular 2D parameter space into a graph paper, and each point on each point of this particular graph paper where one line is crossing another, you can evaluate your likelihood. You can do that. There is no harm in doing that. But one may then ask the question, what should be the grid spacing you should take in your graph paper? How far away you should place your evaluations of likelihood? That would give you a better understanding, the kind of best understanding about your likelihood distribution function. Because at the end of the day, what you are trying to explore is a conditional probability density function or distribution function, whatever way you may want to call it. How will you be able to sample it precisely? So now let me show you some very hand-drawn poor graphs. So let us say this is my underlying probability density function for the likelihood. So I am trying to, or sorry, the posterior. So this is the posterior, that is the quantity on the left hand side of my Bayes theorem. So P of theta given data given a model M. And it has this kind of a weird feature, and I have 2 parameters in my model M, theta1 and theta2, just like before, and I want to basically figure out this particular thing, which is unknown to me. But as it is unknown to me, it is like you are placed in the Himalayan range, for example, where it is extremely foggy and you have only one thing, only one equipment with which you can measure the height. So you can't see anything actually, because it's very foggy around you. You may fall into a crevasse, or there might be a ice wall in front of you. But all you can do, you can measure the height and you can take steps. and somebody guarantees, okay, you will not die even if you fall into a crevasse. So what can you do then? You will take steps in random directions, right? And what you are expecting to explore, you are expecting to explore the peak of this probability distribution. So let's say you were placed somewhere near Gorakhpur, which is kind of the plain, and then you are told, okay, you have to go north, but other than that, I don't know anything about it. I don't know what is the height of different places. So now you can take steps of several kilometers or several meters, several centimeters. But if you take steps of several centimeters each time, you will never reach even the foothills of Himalayas, right? Because you have to cross the Nepal border, then comes the Himalayas. So if you are placed in Gorakhpur border, then you have to take steps of several kilometers, sometimes probably 10-20 kilometers or even more. But if you are placed in, let's say, the base camp of Everest, the first base camp of Everest, then you cannot take steps of several kilometers. You have to then take steps of probably meters, 10 meters or 20 meters, etc. So that is precisely what you do while exploring an unknown, completely unknown to some extent, probability density function that is your posterior distribution. And how it is being done, that is demonstrated here. Let's say you are taking these random steps. So these crosses are your stepping points along one particular parameter axis, let's say. So this is the probability density function for one parameter, not for both. It is kind of a projection. The other one is kept fixed. Let us assume that. So so if you are placed here, you can measure the height of this function. Then if you are placed here, you can measure the height of this thing. If you are placed here, you can measure the height of this thing. And then if you take too large a step, you may miss lots of features of this particular thing. And if you take too small steps, then you might be unnecessarily wasting time. That is what I was trying to say. So these lines essentially represent that your steps are like delta functions, and you are using delta functions to sample a smooth distribution. So what will happen? You will get some sort of discrete sampling, right? So after you collect all these steps or the heights from all these steps, you can draw a histogram, and you can hope, if you have sampled your underlying probability density function good enough, then you can hope this histogram represents quite well the underlying probability density function. And that is the basic philosophy of any sampling, almost any sampling algorithm. So let us get into the Metropolis Hastings algorithm, which is one of the simplest one in this whole suite of things. So what does it do? You effectively are trying to sample this underlying probability density function using an idea of random walk, right? You will randomly move around in the parameter space, even if it's a 1D or 2D or multi-dimensional parameter space. You will move around there randomly. You will evaluate the height of the probability density function, let us call it that, which is effectively your likelihood or your posterior, depending on how you are actually going to evaluate the likelihood, and from that you are going to infer the posterior. So you are going to evaluate the likelihood at each of these points. So what you don't want to waste time in Gorakhpur. You want to reach, let's say, if you want to, let's say, map out the topography of Everest or Kanchenjunga or Godwin Austen or K2, you want to reach the base of those peaks as soon as possible. Then take steps, smaller steps, and explore the features in the peak, because a peak is not a delta function, right? Or it's not a triangular function, it's not a pyramid, it is more complicated. So you want to know all those things as much as possible within the limited computing resources that you have, And most of the time, let's say the limited computing resources means, let's say your laptop, which has just 4 GB RAM, or a quad core processor, or or single core processor sometimes. So you cannot spend months and years to let your random walker takes baby steps from Gorakhpur to reach the base of the Mount Everest. So you need some sort of guidance while taking these random steps. So Metropolis Hastings essentially provides that guidance. So the steps that you are taking, they are random in nature, but there is some sort of guidance being provided continuously. Okay, and also you would not like to have all these steps to be correlated. I will discuss about it later if time permits. What do I mean by correlated steps? But even if you have correlated steps, you should be able to compute the amount or degree of correlation between the steps so that you can make sense of it at the end of all the steps are taken. So let us look at the basic, very, very basic algorithm, and let me tell you, you can write it on your own. Trust me, it is very, very simple. It's one of the most simplest algorithm, to be honest. You just need to know how to generate a random number. That's all. And there are random number generators available within. If you are writing the code in C, there are random number generators in GNU Scientific Library, GSL, you can call them. Even within the math function of C, there are certain random number generators, but they are not that good. If you are writing the code in Python, there are several random number generators available within NumPy or SciPy. Okay, you can use them. So all you need to know is how to generate random numbers, how to evaluate something called log likelihood. That's all. And okay, the likelihood again changes, as you can imagine, changes from problem to problem, because for a given problem you will have a given model and you will have to define your likelihood accordingly. I will come to the likelihood question eventually, but let us, and I will explain it with an example. Okay, let us speed up here. So the idea of a Metropolis Hastings algorithm is that you take only into consideration the probability density that you have evaluated in your previous step to take the next step. So let's say you are at the 100th step and you want to take the 101th step. So 101th step is informed only by the 100th step, not by the 99th, 98th, 97th, 96th, etc. You only care about the previous step, nothing else. And then you basically draw a trial point from something called a proposal distribution, which is centered around your previous step. Okay, we will talk about the proposal distribution as well. And so you can the shape of the proposal distribution or the form of the proposal distribution can be tuned to make the algorithm more efficient. Then you can decide whether to accept the trial point or not, depending on something called an acceptance probability. So you basically take the ratio of the proposal, proposal distribution of the trial point to the previous steps on proposal distribution, and see which one is minimum between this ratio and 1, and choose that as your acceptance probability. So you accept the point based on that. And if the unit, so there is some subtlety that I will come to later. So if the trial point is accepted, then you basically move your random walker to the trial point, you update your step, and then you take the next step accordingly. Otherwise, you go back to your previous step and then again choose a random point from your proposal distribution. That is how you go ahead and do it. Okay, so why this whole business works, because there is something called detailed balance equation, which actually makes sure that the underlying this proportional distribution and the acceptance probability that you are using, that leads to exploring the underlying probability density function that you are targeting to explore. and that is represented by this detailed balance equation. Okay. I think I have discussed these things already, so I will not go into the details of it. Let us just, let us just go into the example. So I have chosen one interesting example to basically demonstrate this particular thing. So you have heard about supernova 1A, which are treated as the standard candle in cosmology, right, to measure distances uh, in the universe. So when you are measuring the distance in the universe, this RZ thing, actually the distance depends on these omegas. These omegas are nothing but the cosmological parameters. So given a cosmological parameter, you will measure a particular distance to a let's say to a supernova or to a standard candle. If you change your cosmological parameter, the distance measure will also change. So now let's say you have some observations of this supernova 1A, some data on the supernova 1A as a function of something called redshift. I'm pretty sure you have heard about this. This is nothing but the cosmological redshift we are talking about. This is not the Doppler redshift. And there is something called luminosity distance. This also you must have heard. So let's say this luminosity distance is measured using a quantity called using a quantity called distance modulus mu, which is effectively measured using the magnitude, apparent as well as absolute magnitude of these supernovae. And within this mu, there is this dl, luminosity distance, where your cosmological parameter contributes, etc. And these things can be simplified. These integrals can be simplified into something like this, where these etas are evaluated through this particular form, where this S is this omega matter. It's a matter density parameter for our universe. Okay, so now given that you have measurements of mu at different redshifts z, a list of redshifts z, you are being asked the question, what are the best fit omega matter and something called H, Hubble parameter, that represent this data, given that you assume your cosmological model is lambda CDM. So that's the question that we are trying to address here. So first of all, you have to then, so what you have to find out, what is the P of theta given the data, right? So here theta are two quantities. One is this omega matter and the other one is this H naught. Sometimes also it is written as 100 into small h, this quantity, kilometer per second per megaparsec. Yeah. So I want to evaluate what are the best fit values of this H and this omega m. Okay, or what are the distribution function, best representative distribution functions of this H and omega m that represent, that suits my data best. So, so I will first write down my likelihood. So to write down my likelihood, I will, because my measurements are mu versus z, that is the measurement. And in this case, I have 31 z values where mu has been evaluated. So I have this mu z data pairs. So the likelihood that I will define in this case is mu. Let us say this mu is running from I equal to 1 to n is the 31, let's say. So mu I minus mu th as a function of zi. So this is also a function of zi actually. Mu I is evaluated at each z. So what is mu th? Mu th is the model prediction for mu. So given a value of omega matter h, what is the prediction from my lambda CDM model at a given z for mu? That is my mu th. Okay. Similarly, there is another quantity mu j minus mu th, which is effectively this is effectively writing as if it's the transpose of the previous quantity. So what I am assuming as my likelihood is a Gaussian essentially, and in between the Gaussian there is this error covariance matrix. Now if I assume that my errors are uncorrelated at different redshift bins, then it will be a diagonal matrix. So basically this will come as a sigma square, mu minus mu th whole square divided by sigma square, something like that. So that is being represented as my likelihood, e to the power of that thing. So generally whenever this kind of e to the power things are there, people get afraid of them, so they take log. So if I take log, then it becomes a simple summation, right? So I will deal with log likelihood rather than just likelihood. So I have these data, and you will get all these data sets to play around with. So here is the data, that 31 sets of mu and z, and this is the covariance matrix, that Cij inverse given, sorry, Cij that is given there. So now let us see how do we write our MCMC algorithm. So I want to take 10,000 steps in my parameter space, and the number of parameters I have is 2. And then I want to define what I have not discussed yet is something called that proposal distribution. So most of the time people take the proposal distribution as a simple kind of proposal distribution. You can take it as a simple top hat distribution or even a Gaussian. So if you are taking it as a Gaussian, take mean around the particular step where you are at, and with a variance. In this case I have chosen sigma. Now the choice of sigma is essentially your step size, whether you are taking 10 kilometer steps or 10 centimeter steps. That is being defined by sigma, and it varies from problem to problem. So you have to basically do trial and error to find out what is the best sigma for you. In this case, I have figured out that this is more or less a reasonable sigma. I have 31 data points, so n supernova is 31. I have defined my parameters in sample. This particular theta array will contain the likelihood as a function of the number of samples as well as the parameters. So yes, this one will be used to store the log likelihood actually. So then, okay. One thing I have not mentioned earlier is from where in the parameter space you start. So I have run out of time. I will just take 5 minutes to finish it off. You can in principle start from any point in the parameter space. So you choose your starting point as from a random point in the parameter space. So I am drawing two random numbers. These random uniforms are essentially random numbers drawn from uniform random variates. I'm starting with a very low value of log likelihood, because I kind of trying to assume that this particular point from where I'm starting is of no significance as such. And eventually my random walker will lead to the significant regions of the parameter space. Then effectively I am opening the file of my data set and reading it in. I am storing, basically arranging the data into two variables z and mu, etc., etc. And just to be, I have also opened the covariance matrix file and read the data. So just to be sure, I just plotted the data. So this is x-axis is redshift, y-axis is mu. So this is how the data looks like, mu versus z. Now I am defining my model. So in the PDF file, how the mu is being calculated through eta, dl, the luminosity distance, etc., that you have seen. So that is being implemented here using these functions. And then I am also defining a function that will calculate my log likelihood. Log likelihood is already that we have defined here in this form. Right. So all those functions are written. Perfect. So I will go ahead and try to just for the sake of sanity check, I will plot different theoretical predictions from my model, basically mu THs from my model, for 3 sets of values of parameters. So omega matter is 0.3 and H is 0.7, the first one, then 0.4, 0.5, 0.6, 0.9. And I just saw that, okay, this particular set looks like the best one, but you don't need to do this. This is just for the sake of demonstration. Then what I did is I started my random walk. So I started with computing the initial likelihood that was already I have set as at a very, very low value here. -1 into 10 to the power 100. So then I am storing this point into my previous, in a variable which stores my previous step. And then I am assuming my proposal distribution around that particular point where I am standing right now to be a Gaussian random, and that is NP random normal actually calls a Gaussian random variable, Gaussian random Gaussian random number generator, and there you are throwing in basically around which the mean value around which this should be distributed. That is your step where you are standing right now, with what kind of sigma that you are also passing, that is 0.01 that we have defined earlier. And same for each parameter, you have to define the specific proposal distribution, and they will throw you, give you some values, proposal values for omega proposal and H. Yeah, I will finish in 2 minutes, don't worry. Yeah, so once you have done that, then you pass those omega proposal and H proposal to your log likelihood measuring function, and this log likelihood measuring function will effectively compute this quantity, log of this quantity, sorry. So, and return you back that log likelihood calculation. Then, depending on what you have got back and this proposed log likelihood, you evaluate the log likelihood of the previous step and check whether this is greater than the value of some random number, some uniform random variate. If it is greater than that, then definitely the next step is acceptable. You accept the next step. And if it is not greater than that, you effectively reject the next step. Okay. And once you do that particular exercise, you end up having a plot something like this, where this is your omega matter, this is your H. You have done 10,000 steps. Okay, I have chopped off some initial 100 steps or so. And this is what the evaluated log likelihood looks like. So the color scheme actually tells you what is the value of log likelihood there. So this is the most likely region of the parameter space where your parameters probably lie. And if you look at the individual, what is called individual probability distribution function for each parameter, they look something like this. So see, omega, it peaks. It is not a Gaussian. It looks like a Gaussian more or less. Maybe you have to have more samples rather than 10,000. You have to make more samples to make it smoother. But it looks like it is peaked around 0.3 or so, which is kind of the best fit scenario here. And in this case also, it peaks around 0.7, the H. And you can also evaluate something called the summary statistics. So you can calculate the mean and standard deviation of this omega and H, etc. Okay, so I will send you these, the Dr. Dotto and others will send you these IPython notebook files, etc., so that you can play around with it and do more things. Actually, that assignment has more problems to solve. Okay, I will stop here. Sorry for running over time.
Thank you, Dr. Majumdar. Since we are running late, maybe we can start with the next session and
yes. I will stop the sharing.
address the questions for later.
Yeah.
Is that okay?
Yes.
Okay, thank you. So the next speaker is Dr. Vargav Vaidya. So Dr. Vaidya, I will ask you to share your screen. And
Dr. Manita, can you hear me?
Yeah, I can hear you loud and clear.
Yeah, great. Thank you. So what I will do is I'll actually share the screen. because I need to share the screen again.
Sure, sure.
Can you see the screen?
Yeah, I can see it now.
Yeah. So can you see the yeah? Can you see the tab with the information about the lecture, right?
Yeah, I can see the MPCST winter school tab.
Excellent, excellent, excellent. Okay, so shall I begin then?
Yeah, let me just introduce him and
Yeah.
then you can. Okay. So, welcome Dr. Vaidya. Dr. Vaidya is assistant professor at the Department of Astronomy, Astrophysics and Space Engineering at IIT Indore. His research interests involves computational fluid dynamics, hydrodynamics, theoretical star formation, particle acceleration in AGN jets, interstellar medium, and astrophysical code development. He has done his PhD from Max Planck Institute of Astronomy in Germany and his master's from IIT Roorkee. Though his research interest involve in computational fluid dynamics, he will be giving you a very interesting and basic introduction on tools for astronomical data analysis, particularly involving AstroPy utilities. So with that, I leave the floor to Dr. Vaidya.
All right. Yeah. I will also maybe start my video, if you can see. Yeah. Hello. Yeah.
Yeah, we can see.
Great. Okay, so good evening, everyone. And I would first like to thank the organizers for giving me this opportunity to discuss and about some very basic topics on tools of astronomical data analysis, mainly focusing on the utilities that AstroPy, which is essentially a package that is developed by the astronomical community all over the world, and it's currently also under development in order to address or actually understand the various sorts of data which are actually obtained from hello, can you hear me? Hello.
Yes, we can hear you.
Yes, sir, we can hear.
Yeah. So based on the different data that you actually have in the astronomy community, in the sense like you can have data ranging from, let's say, spectra of a star, or some sort of time series analysis of some variability in AGN jets, or maybe an image of a star forming region, or basically some sort of catalog, which basically describes as the motion of stars in our own galaxies. So you have data of various kinds, you have data of different quality, different properties. So how do you basically bring all this data under one hood and try to analyze the physics, or try to understand what this data is telling to you? And for that purpose, the community, astronomy community all over the world have gathered together, and they have developed this package called AstroPy, which is a Python-based package. And today we will look into, of course, the time which I have been given is not enough for me to cover the whole AstroPy utilities. But what I will do as part of this lecture is that I will focus on very simple tasks which can be carried out with AstroPy. And of course, this is a notebook which I can share with the organizers, which can be then later on shared with the participants. So they can actually build upon these simple tutorial exercises which I have done here and which you will see, so that you can actually build upon your expertise and become more and more experts towards learning and adopting AstroPy for your day-to-day work. The two references that I have actually followed are the AstroPy Learn platform. They have an excellent tutorial and a documentation, and I would definitely urge all the participants to actually go into details of these documentations, and I will be adopting some of that even in today's talk. Basically, the main examples are based on those tutorials. And then, of course, if you want to become expert and you want to go more detailed into understanding your own data and you're doing some projects, then I would definitely suggest that you should go into documentation part of AstroPy. Just to give you some technical details before I go into the real hands-on tools. The current AstroPy version is 4.2, and it requires a Python version 3.7 or later. and NumPy version of 1.17.0 or later, and PyAirFa, which is essentially a package which deals with essential routines of fundamental astronomy, and 1.7 version or later is required for basically having an AstroPy package working normally in your desktop or in your machine. However, what I'm using here today is a Google Collaborative Lab, which is essentially an online Jupyter notebook, which can be shared just like Google Drive. And it has already installed all these packages, so it's really not required in order to install separately into this thing. But the best, if you want to install it on your own, then the way to do it is using a Python index package. So that's pip. This is actually it's a simple 3-word command: pip install AstroPy. So AstroPy in general basically has several packages and tools which can be utilized to do various things to understand your data, and they can be categorized into different sections. So for example, the first section that deals with data structures and transformation. So essentially here you deal with all sorts of packages that can tackle different sets of data that are available. For example, if you look at let's say our own sun, the light which is coming out is basically in some sort of it gives you a 2D distribution of flux or photon distribution in the plane of the sky. So how do you basically observe these or take this data which is coming from the telescope? How do you basically bring it onto your computer? Along with that, you have to worry about the units, which is extremely fundamental in any, be it astronomy, even in any science, units are of extreme fundamental. You also have option of choosing some fundamental constants, which makes your life easier because you don't have to remember those numbers, and you can just plug in those constants from already existing list. Then one of the most important thing that actually AstroPy gives you, and something which you have already studied in course of this winter school, is positional astronomy. And there you basically deal with time of observations, time and dates. And along with that, you also deal with coordinates, where you have RA, deck, essentially any object in sky can be identified based on some coordinates on the plane of the sky. So how do you deal with those coordinates? How do you basically transform from one coordinates to another coordinates, and sometimes which is required? And how do you basically do all sorts of analysis with your data is something which we will see. Of course, for any data, you also need some modeling and fitting in order to establish some physics out of this or some sort of physical understanding out of it. And therefore, there is also a very nice AstroPy modeling package which can be used. And then, of course, there are other things which are distribution, like normal distribution, log normal distribution, and all sorts of things. And you can deal with them using AstroPy uncertainty. Another important interface or another important aspect of AstroPy, it has a very, very diverse input and output, which is I/O interface, which allows to basically read several files in different formats, which are essentially applicable to astronomy. And that way it allows us to basically read and write data in different formats, and basically you can actually have, the beauty about this I/O is that you can actually have combination of multiple files interoperate with each other, which makes your life much, much simple. So you don't have to convert one data file into another data file in order to read. This interoperability of data is extremely crucial in any package when you are dealing with file reading and writing. So it can handle several files, and it does a much better job. And one of the things which we will be focusing today is the fixed file handling. So essentially, this is a standard files which usually you encounter in astronomy. Of course, then you can do all sorts of computations and utilities. For example, you can do all sorts of cosmology calculations, some statistical calculations. You can also do visualization of different angles and so on. You can do some sort of convolution. So these are various techniques which are available, and they are very much needed. And some of them are extremely crucial to understand aspects related to different problems that you encounter in astronomy. And then finally, you have other more sophisticated algorithms which are related to some utilities and so on, which are absolutely not covered in the above three. Most of the things are covered in the above three packages or above three classifications, but then there are also some other systems which I will definitely not go into details of this. But of course, you are welcome to try the development version, where you can actually, if you are very good at Python, you can actually contribute to this whole community and be part of this AstroPy package. So what I have decided is that since I'm not going to cover everything, I have picked, cherry picked three, what you can say, hands-on tools or some sort of really hands-on stuff that I will do right away in front of you, and we will learn as we go on basically through this notebook, which I will be sharing with all the participants. You will learn what it actually means to deal with these units, coordinates, fits files, and so on and so forth. So this is more like a hands-on session in which you can actually get an experience of what goes underneath when you want to analyze or see the data, or even do some sort of statistics or some sort of fitting with the data, right? So the first, so basically I have broken this lecture into three different cases. So the first case is we will play with units. So these are of fundamental nature. Remember one thing in astronomy, we astronomers tend to like, or actually like, to deal with CGS unit systems. So it's always very good. But in addition, we astronomers also make everything confusing by adding more and more units like magnitudes and some sorts of Jansky, millijansky, though they are related to the CGS units, but they make it much more complex. The unit framework becomes much more complex. So the first task, we will be dealing with very simple units and how to basically access those units using AstroPy. Then we will be playing with some coordinate systems. How do you convert from one coordinate frame to another coordinate frame? And then we will demonstrate how we can use such coordinate frames to actually get the observation time and observation angle and so on and so forth. And finally, since I said earlier in the lecture, FITS files are of extreme crucial importance in astronomy, as most of the telescopes output images or data or tables in terms of FITS files. The idea is to how to play with these FITS file using AstroPy. So these are the three tasks that we will be carrying out throughout this in the next 20 to 30 minutes, 20 minutes or so, and we will see how actually it goes on. But I would urge every one of you to basically, when this notebook comes, play with it so that you will get more and more experience of handling data and units and coordinates and various other things which are not covered in this part of the course. So let's start playing with the units. So AstroPy units, if you want to invoke AstroPy units, the way to do it is from AstroPy import units as you. This is essentially, this is just to import this package, the units package, astropy.units package. It handles defining, converting between, and performing arithmetic and physical quantities such as meters, seconds, hertz, etc. It can also handle logarithmic units like magnitude and decibel, which is essentially magnitude is something which is used as a unit to define the flux of a star, and decibel is to define the power. So a very simple example, if I basically just invoke this units, then you have all sorts of, so this is like a module. This subpackage contains classes and functions defining and converting between physical units. So you can just have a look at this. But the simple thing is, what I've defined is L is 10 centimeters. So L basically is a quantity. So L is a quantity. It's not a number, it's not an integer or anything, it's a quantity, and it is 10 times u dot cn. So if I basically now print L, what it gives me is 10 centimeters. So that is what I'm expecting. Now, if I want to, let's say, convert this L to, let's say, in kilometer, then it's very simple. You just say L with an attribute 2, which basically converts this unit and equivalencies. And what it does is it converts into unit.kilometer. So you have unit.kilometer, and when you do this, essentially it converts this unit into kilometer, and that gives you 10 to power minus 4 kilometers as expected. So this is this shows you how easy it is to convert from one thing to other. So this is just a simple example focusing on one unit, but you can of course do all sorts of computation. So here is a very simple a simple snippet of code which basically takes the velocity. So I have some velocity of some body of mass 2 grams and velocity is 10 meters per second. So essentially, see how meters per second is defined. 10.0 unit of meter divided by unit of seconds, and mass is 2 times unit of grams. And now what you want to do is you, let's say, estimate the kinetic energy. So if I basically estimate the kinetic energy is 0.5 mv square, and let us just print the kinetic energy. So I'm not printing anything, I'm just printing the kinetic energy. So if you print the kinetic energy, that is 2 times 0.5, that is 1, and 10 square, which is 100 grams per meter square per second square. So essentially, when you just do this quantity estimate, what it does is it basically computes whatever units is just blindly multiplies these units. But of course, we know that the kinetic energy typically in CGS units has the units of erg. So we can always convert this kinetic energy to unit of erg in this form, and then we can print it, and what it will give you is basically the value in ergs. So this is how you can actually play with this thing, and you can be relaxed that you will not mess up when you want to convert from one units to other. So that way the functionality of units is extremely powerful because it helps you to be more dependent on the software, but it also helps you to give you more accurate understanding of different unit conversions. So with this simple example, we can go to slightly more complex example where we actually now are dealing with a much more physical problem, where I would like to estimate, let's say, the total luminosity of the star or the total flux coming out of the star, by assuming that, say, it's a black body object. It's basically emitting like a black body. So what we'll do is for black body, of course, AstroPy has all sorts of functionality available in astropy.modeling, and this is how you can actually get from astropy.modeling black body. You can get black body underscore lambda, which basically is the black body function in terms of lambda, or black body underscore nu, which is essentially black body as a function of nu, and this is black body 1D, it's just 1D function. Again, here I am basically saying units and constants. So here you also have constants available, and you can have all sorts of things. So now, if I want to basically, what I will do in this case is, first I will plot using this AstroPy modeling the black body function as a function of nu for a given temperature, and then what I will do is I'll integrate this and basically get the units accordingly. So here is another example. Here there is another thing that when you actually define, let's say, this np.lim space from 1 to 3000 with 1000 points, essentially it's an array. So when you multiply this with the units, each element of that array is actually given that particular unit. So that way actually it gives you a very nice way to also define the whole array in terms of units. Then what you can do is you can define this black body function at 5000 Kelvin. So again, this is the quantity. The temperature, note, it is given in terms of Kelvin. So unit dot Kelvin, again we are using unit dot Kelvin with 5000 Kelvin. And this, what it does, it basically computes the black body function for the given frequency and the temperature. And then what you do is you just plot this thing, and you give all sorts of names to this. So for example, you can always get a unit of any function, of any complicated function, using dot unit. So that way it's also fine. Nu dot unit. So nu dot unit is basically terahertz, and it will be the unit of the flux. So now if I basically do this, it will compute, and it will basically give you the nice black body spectrum as it is. Where nu, now note, the unit is in terahertz, which is basically coming from here, nu dot unit, and the I nu, which is the intensity, is ergs per hertz per second per steradian per centimeter square. So this is basically your I nu associated with for the black body spectrum. Now, if I want to integrate this, okay, so if I want to integrate this for all frequencies, I can definitely use np.trackset, which is the most simplest of this thing. And then remember, once you integrate this thing over all frequency, the hertz goes away, and what remains is ergs per second per centimeter square per steradian. So then what you do is you integrate this thing and then you transform it into the units that you want to have. And then once you do that, you essentially have the value that you want. This is essentially Earth per second per steradian per centimeter square. So this is how you can actually utilize the units and the constants. So in this case, many constants can be used. For example, if you want to do h nu by kt, you can use these constants as well. But essentially, the idea is that using units, you can do a seamless transformation between one quantity to other quantity and get all sorts of physics going on. Okay. So that's of course there are several other applications of units and so on, but this is just to give you a brief idea of how these things works and what are the main functionality of this package. The second task that we will be carrying out today is essentially playing with coordinates. So AstroPy coordinates, as I said, is a sub-package that contains of classes and functions, mainly in Python, for celestial coordinates and astronomical objects. And these are extremely crucial in order to do any sorts of observation studies or any sorts of comparing with catalogs. So for example, you have one catalog having let's say coordinates in galactic coordinates, so essentially in terms of L and B, whereas there is another catalog which is giving you an RN deck. So how do you do cross matching of these catalog when you have coordinates in two different frames? So you need a lot of conversion between these coordinates, and AstroPy gives you a very seamless package for such kind of conversion and such kind of extracting coordinate system. So when we are learning about the coordinates, so again we will focus on very simple example here. Now the aim of this exercise is to understand how AstroPy extracts the information of given sky coordinates. So I have one object. So essentially this object is what I've chosen here is Higgson compact group 7. So Higgson compact group 7 are essentially Higgson compact group objects are essentially collection of galaxies spread over the sky, and very low redshift galaxies. And then the point is that you have the RN deck of each of these compact groups, like they range from 1 to 100 or something like this, and you have centers of each of this in terms of RN deck. Now I want to basically extract that Higgson compact group object given the RN deck and try to plot that image in front of me from SDSS database. So that's the aim, or that's the plan. So for that, I basically depend on some standard libraries to retrieve the URL. Given a URL, I would like to retrieve or download that data. And then you essentially have AstroPy coordinates, which I am using. So this is the way to invoke the AstroPy module, and I'm using the sky coordinate attribute to it. And then, of course, if I want to display the image, I'm using the IPython display image. Now, what is cool about SkyCoord is basically from the name itself, you can actually get the coordinates. So, for example, HCG7, the Higgs compact group 7, this is the name of the source. Just from that source, you can extract this thing. So, for example, I can give this, and SkyCoord is not. Oh, first I have to basically run this. Yeah, so that's my fault. First I have to run this in order to compile the SkyCoord, invoke the SkyCoord, and then I'm able to basically, yeah. So I'm now able to run this. So now what you can see is that HCG7 underscore center basically has the SkyCoord. So you can see what it is. So you can see it's an AstroPy coordinate, sky coordinate, which is a SkyCoord. Okay, and SkyCoord is basically defined in one particular frame, and in order to have any functions or attributes of this particular sky coordinates, you can have a look at it of what are these things. So there is a list of things. For example, in this case, it's RN deck, but you can convert it into, let's say, a galactic into galactic frame or galactocentric frame, or many. So this is ICRS. You can even convert to HCRS. And many other. You can convert it into LSR frame and so on and so forth. So this is HCG7 underscore center. But what you can also do is you can print this thing. So here you can see this is basically the RN deck. So it's 9 degrees, 48 minutes and 58.5 seconds, and it is 0 degree 53 minutes and 17 seconds. You can also print it in terms of hour, because RA you basically get in terms of time, so you can even print it in terms of hour, and this is 0.655 hour. So this is the way you can actually get information about RA and DEC of this. And if you look at the type, so type basically tells you what sort of object this is, and it is essentially astropy coordinates angles, longitude and angles latitude. So essentially HCG 7_center RA is an angle and DEC is an angle. So by default it basically gives you an angle, and similarly you can always convert this into an hour as well. So this is in longitude, so this is in terms of degree, where you basically can get everything in degree, or in terms of hour. So this way you can actually play around with it, so you have information in all sorts of RA and DEC. So it's not always required to basically give some object name. You can choose, sometimes the object name is not defined or sometimes. So you can in general give any RA and DEC value. So for example, with this frame ICRS, which is the standard frame and the default. So here also you can basically give ICRS, and it gives you values in degree. So here it is the typical way to write hours, minutes and seconds. But in general, AstroPy converts the sky coordinates and gives you RA and DEC in degrees. Okay, so now for HCG 7 center, we already have the value. What we can do is that now what we can do is we can extract this information and try to see how this thing works out. So this is a simple code. What it does is it goes through this HDSS database and tries to catch out this thing, and it saves it into a JPG file. And now what you can do is then you can basically read the JPG file, and you can see this beautiful image that comes up with multiple galaxies. Here is a spiral galaxy, another spiral, more elliptical galaxy. So this is the Higgs compact group 7 object, which I have, by the way, extracted from the database given the RA and DEC. Okay, so and also here I'm using the arc second. Note, I'm converting my image size to arc second. So that way actually it gives you a very nice and automated version to basically extract images. Similarly, you can play around. Now that I know the RA and DEC, I can basically give the RA and DEC for HGC 7, and it's very simple to actually convert this RA and DEC in ICRS frame to galactic plane. Okay, so galactic coordinates. So what I just do is HCG 7 and dot galactic. What it does is it converts this now into sky chord galactic. Remember, before it was sky chord ICRS frame. Now it is sky chord galactic frame. And note that now it is not RA and DEC, but it is LNB, which are essentially your galactic coordinates in degrees. Again, 116 degree and minus 61.8 degrees. So this is one way of converting from RA DEC to galactic. Or you can basically just import the galactic base class and convert him in this manner. So it will again give you the same value. Or you can basically do the transform to function to compute to convert it into galactic framework. So these are the ways to convert your RA and DEC into galactic coordinates. Of course, you can transform from one frame to another. There are several of them: ICRS, FK5, FK4. Yeah, there are all these things. One interesting thing which I would like to actually highlight is altitude and azimuthal, because see, usually in astronomy when we deal with coordinates, we always deal with RA and DEC, because these coordinates are independent of the position from where you are observing. But typically when you are looking at an observer, you always want to have the values in altitude and azimuth. Okay, so we'll try to see how we can convert this HGC 7 center into altitude and azimuthal. But before we do that, there's one important thing, that when you transform the coordinates from one frame to the another frame, it is not necessary that the attribute of the earlier frame remains. So for example, HCG 7.center.RA was existing, but HCG 7.galactic.RA is not existing, because For galactic coordinates, you don't have RA defined. You essentially have L and B defined. So in order to get that, you have to basically define L and B. Okay. So now, as I was mentioning, that you have now your altitude and azimuth coordinate systems depend on the what you can say, they depend on the position. So astropy coordinates has a very interesting function, which is essentially called Earth location. So with Earth location, you can actually give the latitude and longitude of your place along with the height in terms of meters. And of course, here I am also using another module, which is astropy time, to get the time converted from UTC into local time. And what I am doing here is that you can basically describe your location, and you can basically have the location of Kitt Peak, which is in Arizona, and you can basically then calculate the azimuthal and altitude based on that particular location. But the beauty is that Earth location also gives you different site names. So there are already existing sites of standard observatories like ALMA, DKIST, Gemini North, Gemini South, Greenwich, JCMT, Kagra, all sorts of are available. And of course, it also has an Indian satellite, Indian observatory, which is the Vaini Babu Observatory handled by IIA. So you can also then now define PB as the Earth location of site, this thing. So it essentially, you get the latitude and longitude of this particular site. And then you can define, let's say, observing time of today at 4 p.m. UTC. So to note that this is usually time in UTC. So then you can basically define, let's say, the observing time is today. Then what you do is that you can basically now import the alt azimuth class, and then you can define this AA coordinate frame, which is alt azimuth. Location is given by this BB. Observation time is given by the observing time. So now you can basically have the print AA. What it gives you is the observation time, the location, okay, in terms of this pressure. These are all the information that is there for the Earth location. Now, if I want to now convert this, which was HGC 7 center RA deck, into AA frame, what I do is the following. So it converts it into this thing, and now what I have is basically the alt azimuth in degree is 269 degrees and 7 degrees. So I can print them separately out as 7.25 degrees and longitude of 269 degrees. So this is how you can actually convert your RN deck into what is basically location specific thing. And people actually plan their observations, especially optical observations. If you want to focus on one particular object, you plan these observations based on these conversions and try to see if your object is where your object is in the sky based on the observing time, based on the location, and so on and so forth. So this is just give you an idea of how you can actually do such kind of calculations. And finally, the last task which I would like to focus on is something which is very fundamental to astronomy, because most of the files that you receive in terms from observatories or even the exchange of files are usually in FITS format. So the package that we will be invoking is astropy.io.fits, which essentially provides access to the FITS files. FITS is essentially called flexible image transport system. It's a standard widely used in astronomy community. Okay, so this is something which I will do. The beauty about the FITS format is that it has two aspects. One is that it has a header information where all the information about the image is stored, from which observatory it is taken, what is the pixel width, what is basically the observational properties over at that time, what time, what place, everything is there in the header information, and then there is the data information. So in order to invoke this, it is from astropy.io import fits. So let me import that. So once I import this, then basically what I will do is I will download a file. Again, a download file is basically an option available, and I can download this file from utils.data. So this is now going into the nuts and bolts. So a download file is available, and I'm downloading some FITS file from the repository. And now once I have that image file stored in my thing, what I can do is I can open that image file using fits.open and look at the information over there. So what you can see is that you have an information which is given as so you basically have the primary information and table information. So this is basically the primary is where all your data and everything is stored. So the primary information is an image of this dimensions, and it has a format of integer 16. So it's an integer format. And if I want to basically access the data from this, that what I do is basically I just run an image data, and image data basically is stored now over here. And now I can have a look at what all this image data is. So of course, this is image data now is a NumPy array of size 893 by 891. So that's the information that you actually get from here. And then we can close the file. So now you have image data has all the data that is relevant for you. There is another shortcut method. For example, if you don't want to go to the hassle of looking at the info, you can directly get the get data, which is image data equal to fits.gets data image file. So the image file is basically the file which you have downloaded, and then it will again be the same. So this is another short way of getting the data. So now if you have the data, we can always look at how to plot it. So we can basically just plot that data, and then you can see a beautiful Horsehead Nebula fits image can be seen here. You can basically see how this dark star forming region of Horsehead Nebula, which is the fits file from the data that we have. So this is the way one can actually obtain the data. I will take I'm running out of time, but I'll take just 5 more minutes to show some more information of how this data can be analyzed. So of course, one can do all sorts of statistical analysis like NP min, NP max, mean, standard deviation with the image data. So you have an image which is a NumPy array, and you can do all sorts of measurements and so on. So you can get all the mean values and the max values and standard deviation and so on and so forth. You can also basically plot the histogram of this particular data just by using this flatten structure. What it does is it converts this 2D image into this 1D line. So it's a 1D image, and then basically I'm doing the binning, auto binning, and you can basically see how my image pixels values are kind of distributed in different values. So basically these are just an histogram of the image that I have, and these are the values which are kind of plotted. If you are interested, you can also convert it into log norm. So basically it's just a different scaling of image. Instead of having a linear scaling, you can have logarithmic normalized scaling in the for the colors. And then what you can do is that you can actually plot this with a different color bar, and you can see how it looks like with the logarithmic scaling. You can clearly see this Horsehead Nebula feature, which is actually coming up, and with brightened structure where your stars are forming inside these things, and then there is also bright emission on the outer part. So, and of course, I've used a slightly different CMAP, so you can play around with this CMAP and get more and more beautiful colors as you wish to have. And finally, the last part that I wanted to cover is basically if I want to write my own fits file, how can I actually do that? And so what I do here in this exercise is that I download several fits images of one particular source, which is M13, which is Messier 13, which is a globular cluster, M13. What I would like to do is that I would download all these fits file using this simple code. And what I will do is I'll stack these files. So essentially, I'll keep on adding these files on top of each other to create a stacked image. So essentially, it's an image which has contribution from all these files. And so the way to do it is, it's here. What I'm doing is I'm creating a list called image concat of each fits file. And then what I'll do is I'll basically just add the data inside the for loop. Okay, so this is the long way of doing it, but of course you can use np.sum access 0 and do this. And then if you basically have generated this stacked image now, What I'll do is I'll plot the histogram just to see how it looks like, the histogram. And what you can see over here that the histogram is kind of peaked around 2500, whatever is the value, the value pixel values. And so now I can choose my Vmin and Vmax between 2000 and 3000, and I would like to see how my image will look like, the stacked image looks like. And it basically looks like this, so it's much more smoother. If you look at each of the FITS file, it's far shaky because of the turbulence. So if you basically stack all these images, you actually get rid of a lot of turbulence due to atmosphere and try to get a much sharper image. And of course, you can play with your Vmin and Vmax, so you can increase this slightly so that the contrast changes. So this is how your contrast changes and so on and so forth. And then the important point is that if you define like an output file, which is like a stacked M30 blue in the blue line, what you can do is you can define your HDU as primary HDU final image. The final image is basically this particular thing where you have the final image is the sum of all the images. And what you do is you just say write to out file and overwrite equal to true, and you will generate a new file which is the stacked M13 blue FITS. So this is how you actually work your way through several. At least I have given you an idea about three different modules in AstroPy, of course combining several other modules. But of course, I will share this Google Notebook with everyone, so everyone can have a look at it. Everyone can build on this and work your way through. So I'll end my talk here, and we can take questions. Thank you so much for your attention, and thank you once again for the organizers for giving me this opportunity. Thank you.
Thank you, Dr. Vaidya, for giving such a interesting talk. So it's now open to questions. So if you have any questions, please feel free to type in the chat box, or you can raise your hand as well. For both sessions, I think Shuman is also here. Yeah. So there is a question, what is the source of the data sets? Is it from Kaggle or other source? Oh. Bhargav, I think this is meant for you.
Okay. Yeah. Sorry, I was muted. Yeah.
Okay.
So Supratim, this data which I have actually demonstrated here are from the data.astropy.org tutorials. So they have basically a collection of data of FITS images, and mainly for tutorial purpose, and that is what I have utilized for this thing. But of course, you can get all sorts of data files from different observatories or some archival data which are available in FITS format. Or the best way to look at is there are these catalogs like Simbad and Vizier, which have storage of astronomy databases, and you can have download these FITS file from there.
Any other questions? In the previous talk, why did we use that inequality relation to move from the previous step to the next step in the image sampling? I actually missed the explanation. Dr. Majumdar?
Okay. So why did we use the inequality? Okay. Let me just go there. Just a second. So basically what we were doing there, we were evaluating the proposal distribution at 2 points. One at the previous step and one the proposed next step, right? Then we were taking the difference between them, and we were seeing whether that difference is equivalent to something completely random, how probable that difference is, let's say. So if you remember that we defined something called acceptance ratio. So to evaluate that acceptance ratio, we were taking the ratio of the proposal distribution at the previous time step and the proposed next time step, and probability of the proposal distribution from the previous time step and the next time step. And there was also one. So if, let's say, the next time step is more probable than the previous one, then we will then the ratio will be greater than 1, and one number there will be one number greater than 1, and then there is 1. So I will definitely choose an acceptance probability of 1 and move to the next step. Now what happens if it is less than 1? Should I discard that particular step? The answer is no, because then I will basically lose lots of steps, because there will be many steps which are less probable than the previous step. So whether that particular step is of any significance or not, that we decide based on a comparison between that ratio, which is less than 1, and a random number drawn from a uniform random number generator, whether this particular point is of any significance or not. So we compare these two numbers. That's why the inequality, whether this uniform random number that is being drawn is greater than this ratio. If so, then we do not go to that step and stay back where we are, or if it is not, then we move forward. So it is kind of a decision making step, nothing else. Yeah. I hope that makes sense. But yeah, this is, I think once you get the slides, it will be a little bit more clear, because things are written in a more coherent fashion there, I guess. Yeah. Sorry.
Thank you. Any other questions? If not, we can thank all the speakers of all the sessions, and we end today's lecture session here.
Okay.
Thank you.
Thank you so much. Thank you. Thank you.